This is the high spot of the. Hope Zoom people are with us. This is the high spot of the conference. It's the J.D. Bullock Poster Prize, thanks to the generosity of the what's this? Oh, sorry, Janet. Royal Society of Chemistry Biotechnology Group, who've donated £150 to this award. So well done. I'm not biased, of course. So, and the award of a certificate. Now, we've had 5 poster presentations, and 3 stood out in particular. No offense, Chaz or Mark, you guys. There was the one by Vrije on high-resolution strontium isotope analysis of Bronze Age cattle from Cambridge. This was an engaging story, looking at the moulders of these species. But it was well presented, very clear. We understood exactly what the study was about, and the results were very good. Then there was Madeline's poster talking on cross-channel communication, and it was a nice example of combining isotope with genetic ancient DNA analysis, and that's almost ready for publication from what I've been told. So that was again very clearly presented. This is what we thought as a panel anyway. We were very impressed. And then there was John's poster looking at the traces of Roman coinage based on a combination of silver and lead isotope and other elemental analyses to give the story. And there was a very interesting correlations that you did. Now, it's taken us some while to try and sort this, because we thought the 3 of you were excellent. So in the end, we decided to split the prize between the 3 of you. So I don't think we can go back to the biotech group and ask if they could multiply the 150. So I'm very pleased to say that all 3 of you are joint winners of the J.D. Bullock Poster Prize. So if you want to come up and get your certificates. So, John, Riley, and Maddie. So, on behalf of the committee, the group, well done. Okay. Peter, did you get that?
Yeah, one last question. Excuse me,
Thanks, Peter. Okay, so now Chaz is running away. Oh, Gilberto's, yeah, you're chairing this session. Yeah. So, and the first speaker is Janet, but that's your job.
Liz is not talking from remote.
Was Liz? Yes.
Liz is talking from remote.
Right. Let me just check if Liz, are you there?
Yes, I'm here.
Fine. Sorry about that. It's because Janet's slide went up first, and I was a bit confused. So yeah, it's you. So right, if you can, you're going to load your talk up by share screen.
I'm going to share my screen. Yes.
Okay.
Hopefully, you can now see that.
Yeah, we can. I'll just put on the presentation mode.
Yep.
Right.
So that's
And my bit of sharing. Liz Bailey, University of Nottingham, the merits and quadrupole-based mass spectrometer for isotope analysis. And the floor is yours.
Thank you very much. Yes, I'm a member of the Agriculture and Environmental Science team at the University of Nottingham. And what I'm going to talk to you today about is the merits and the limitations of quadrupole-based mass spectrometers for doing isotopic analysis. And I will say that this is part of a group effort. Many of my colleagues I'll acknowledge at the end. So thank you. So I know that quite a lot of the audience will be very interested in the determination of isotopic ratios, and you've probably used a variety of techniques to determine those ratios, including thermal ionization mass spectrometry, and possibly some inductively coupled plasma mass spectrometers, including high resolution magnetic sector instruments, multi-collector instruments, but probably none of you have used quadrupole ICP-MS for the sorts of isotopic ratios that require high precision and high accuracy. And each technique has its own advantages and disadvantages for the measurement of isotopes. And traditionally, quadrupole isotopic ratios are considered to be less precise and accurate than those determined by other methods where masses are measured simultaneously as opposed to sequentially as they are in a quadrupole ICP-MS. So if I just briefly summarise the advantages and the disadvantages of the techniques, thermal ionization mass spec, the most precise technique. But the disadvantages of using TIMS is that there's quite a lot of extensive separation required of your sample to remove matrix effects. The analysis times can be quite long. And because of the sample introduction and handling techniques, you can lead to the risk of contamination of your samples if you're not very careful. Multi-collector ICP-MS has slightly lower precision, but is still very sensitive and is quite good for the accurate measurement of, for example, lead isotopes, but still requires quite a lot of sample preparation and often manual sample introduction to be able to get the best ratios that you can. And quadrupole instruments, well, they are relatively inexpensive instruments. They're very commonly used. I have 2 in my laboratory myself. And they're very simple in terms of the sample preparation, handling of samples and the operation of the instruments. And they have a high tolerance to the sample matrix. But as a consequence, they have the lowest precision and accuracy, probably for things like lead isotope measurements. That accuracy and precision is limited by noise in the signal, so variation in the signal intensity. And that arises from a number of sources with a quadrupole instrument. So it'll arise from your sample itself, typically the sample matrix, variation in the total dissolved solids in the sample and between the sample and the standards. And then you have the ion source, you have the nebulizer and the spray chamber system that's used to introduce your sample into the plasma and the plasma itself. And then you have an interface region where you have optics for focusing the ion beam, and sometimes a collision or a reaction cell that might be primed with different gases, etc. And then you have the quadrupole mass filter that can introduce noise, and then the detector itself. Now, the detector for a quadrupole instrument is a discrete dynode detector, typically, and that necessitates a compromise between employing large analyte signal concentrations to improve counting statistics of the minor isotopes, whilst working below the point at which that detector is going to trip from pulse counting mode, which is the mode you want, into analog mode, because it can't cope with the signal that's coming at it and the number of counts it's receiving. And the other factors limiting quadrupole ICP-MS in terms of isotopic ratio measurements are spectral interferences. For example, atomic and molecular ions with a similar mass to charge ratio to the analyte that you're interested in. and maybe iron bursts arising from nanoparticulate species that might enter the plasma that you've got to consider. I will say that iron bursts are generally very well handled by the electronics and the software, so not too much of a concern. So because we're interested in being an environmental team in pollution, we wanted to understand how much we could optimize quadrupole ICP-NS for the determination of isotopic ratios to use, for example, in source apportionment studies. So how good could we get the technique? So we set out to investigate that. We had a PhD student who did most of the legwork, and the focus here was on optimizing lead isotopic ratios in particular. So how did we do it? Well, we took urban soil samples that we knew would have lead contamination in from the cities of Nottingham and Wolverhampton, and they covered a range of lead concentrations from about 28 to 900 milligrams per kilogram. And we digested those as we normally would in our laboratory in hydrofluoric acid. And the first thing we did was measure the total lead concentration in those samples. Now, the precision of a lead isotopic ratio measurement is generally going to improve with increasing lead concentration because your counting statistics are going to improve. But as I've already alluded to, at high concentrations, there's a danger that the detector on the quadrupole instruments will trip into its analog mode, resulting in non-linearity and the different isotopes being measured in different modes. So we wanted to avoid that happening. So we set out to standardize the lead concentration in all of our samples. So having measured total lead, we then did bespoke dilutions on each sample to bring the concentration to a near identical concentration of about 15 micrograms per litre. And that was below the point at which the detector would trip into analog mode, but as high as we could push it to maximise the signal of the lead-204 isotope. So by doing that, we were also reducing the effect of any error in the detector dead time correction. So where the detector is getting counts, there's a little bit of dead time where when it's recording one count, it can't measure another count if it arrives at the detector very shortly after. So there's a correction there for that. And we were maximising, as I said, the lead-204 signal whilst keeping the lead-208 below the detector trip point. So that's how we optimised the sample factors, but then we optimised a number of instrumental factors as well. So that detector dead time correction, we investigated with a series of standards for each of the isotope pairs, and we optimised the isotope intensity ratios against the intensity signal of lead-208. And we varied that dead time correction factor until the value of the slope squared was minimised, and then we averaged it for each of the isotopes. And we did that before we used the instrument to make any isotope ratio measurements, so at the start of the day before any run. We also had to do a mass bias correction. So first we took our lead isotope ratios and we corrected them for any interference on the lead-204 signal for the mercury-204 signal, and operational blanks we used as well. So the data that we then got, we corrected for mass bias, so different masses of the isotopes, using both proxy internal and external standards. So for the internal correction, we teed in a 2 microgram per litre solution of thallium into the sample line. So we could use the fact that its isotopic masses of 203 and thallium-205, which were very close to the lead isotopes. We could use those as a proxy for continuous monitoring of mass discrimination in individual samples. And then we also did an external correction using the NIST standard reference material 981 material, whereby we ran that solution every 10th sample to allow us to do a linear correction by interpolation between those two values across the intervening samples. We investigated the dwell time that the instrument should record at each isotope, the time it would sit at each isotope before moving on to the next one. Obviously, you want it to be long enough to maximize the counts, but not so long that the variation in the plasma as you move from one isotope to the next sequentially becomes too much of a problem. And we also investigated peak compression mode and not using peak compression mode, and found that that actually made very little difference. So I won't say anything more about that. So in the table on the right-hand side of this slide, I show you the optimized parameters, the isotopes we measured. And we were down to an analysis time per sample of around about 16 minutes. So we measured the isotope ratios using this optimized method. And then we gave some of our digested samples across to colleagues at the British Geological Survey, who then undertook a further lead separation methodology. So they passed it through an ion exchange resin, etc. And they measured isotopic ratios on their multi-collector ICP-MS instrument. So what were the results? How well did we manage to optimize the quadrupole method against the accepted multi-collector method? Well, here I show 4 isotope pairs for you. And if you look at the graph on the top left here of the 206-207 ratios, we've got the multi-collector data on the x-axis and the quadrupole data on the y-axis. And you will see that for the 206-207 and the 208-207 ratios on the graph below, that we got really excellent correlations and very, very good agreement with the multi-collector instrument. The graph at the right at the top there shows the lead 208-204 ratios. That was also fairly good, but a bit weaker than the other ratios I've just mentioned. But it's perhaps understandable why that ratio should be not quite such a good correlation. There's a greater dependence on mass bias because there's 4 mass unit difference between lead 204 and lead 208. We've got the very low isotopic abundance of lead 204 at just 1.4%. So that gives a lower signal and poorer counting statistics. And the large difference in isotopic abundance actually makes there's an increased vulnerability to errors in the dead time correction there. And then, of course, the lead 204 signal needs to be corrected for mercury, any mercury 204 that might be present. Now, the fact that we digested our samples by hydrofluoric acid reduced that problem with mercury. We were able to optimize for a couple of the other factors. So the dominant and unavoidable factor is the lower counting statistics for lead 204. And we see this again with the lead 207-204 ratio on the graph in the bottom right-hand corner. Lead 207 is the second least abundant isotope at about 22%. So there's, both of those produce poorer counting statistics, and therefore the ratios that you get for 207-204 are the worst ones that we observe. But nonetheless, with the other ratios being quite comparable to multi-collector, that does allow you to go on and do a whole host of things with isotopic ratio measurements just from a quadrupole instrument. So here is an example of a source apportionment study we did looking at lead isotopic ratios in whole soils. We were looking at lead lability, so how mobile lead was in soils, and we took soils from a range of diverse origins. So we took rural roadside top and subsoils. We took some soils from a dedicated sewage treatment farm near Nottingham, and some the study also used some samples from an archive collection of London urban soils that the British Geological Survey held. We covered a huge range of lead concentrations for about 14 to 23,000 milligrams per kilogram lead. And here we're plotting these samples on a binary diagram at 208, 207 against 206, 207. And some of the samples will plot near the geogenic ratios of UK ore and UK coal, which are up here on the diagram. And then as they have an increasing amount of petrol-derived lead present, they will plot towards the petrol-derived lead signature. Now, petrol in the UK used to have the anti-knock agent, tetraethyl lead additive, to improve performance. That was banned several decades ago, but nonetheless, there was a lot of lead of quite a unique isotopic signature released in the environment. And so we can use that information to assess the amount of lead from petrol in our samples. So we used our optimized method to derive this data with quite a lot of success. We also applied the method to looking at the contribution of lead sources to plant uptake. So here was another study where we were looking at that sewage farm just outside Nottingham, where they've been applying biosolids from the sewage to arable soils in the vicinity of the farm. And different fields have had different amounts of biosolids added to them over the course of about a century now. And so different fields have different levels of lead contamination. And we measured the isotopic ratios there, and you see quite a lot of the samples are moving towards the petrol lead isotopic signature. And if we look in a little more detail at the soils on the left-hand side here, as the soil lead concentration increases, so does the proportion of lead derived from petrol. So we have the ratio in ore at the top here, that dotted line, and below the ratio in petrol. And so as total concentration increases, we're seeing much more petrol-derived lead. The figure on the right compares petrol-derived lead in soil with that in the maize crop that was growing on that soil. And at high levels of petrol-derived lead in the soil, the isotopic signature of the lead is similar to that in the plant. They fall on this line quite well. However, the ratios increasingly diverge at low proportions of petrol-derived lead. So the sample shown in this red circle here. And that's a reflection of the fact that the plants are not readily taking up lead from the soil. There's a low root affinity for lead and low solubility of lead in soils. So what's happening here is that the lead contamination in those field crops, in that maize, is originating mainly from external dust. So what we've got is that a small amount of dust from a neighbouring field with a large lead soil concentration, and therefore a higher proportion of petrol-derived lead, is significantly affecting the isotopic signature of plants growing on the soil with a low lead concentration. So the converse isn't, of course, true, because dust from soil with a low lead concentration will have a negligible effect on the isotopic signature of plants that are growing on a soil with a high lead concentration. And so the net result is that inevitably the range of isotopic signatures in the plant is actually narrower than that which we see in the soils, and shifted towards that of the signature of petrol lead. Oops. So just so that I'm not talking solely about lead isotopes, I just thought I'd throw in a couple of slides to show you our work on uranium isotopes, coming from a project where we were the radioactivity in the environment project that NERC ran a few years ago. We were working on soils from the Chernobyl exclusion zone, and we were interested in whether there was the presence of any uranium fuel particles from the explosion in the forest soils around the Chernobyl reactor. So colleagues collected soils with variable levels of suspected contamination in them and brought them back. And those soils were first of all taken to the British Geological Survey, where Lorraine Field collected some autoradiographs to look for gamma-emitting particles within the soils. So here she's put the dried sieve soils, spread them out to form a very thin layer, and then she measured autoradiographs over the course of a weekend. And these very red spots that you can see represent those strongly gamma-emitting particles in those soils. So then we digested the soils and in aqua regia and measured uranium isotopes on those soils and plotted here the uranium-238 concentration against the uranium-235. And what you see in red on this graph is the dotted line. It's the background isotopic ratio of about 138. But some of the soils are deviating away from that line, showing enrichment in uranium-235 and confirming that those gamma-emitting particles observed in the soils were likely to be fragments of fuel rod particles that were released in the explosion on the 25th of April 1956. And were that data just random scatter, we'd expect to see points below the line as well as above them. And from that data, we can actually accurately quantify the concentration of uranium from fuel rods in those soils. Okay, that was a slight aside. So I just want to say in summary, quadrupole ICP-MS, definitely very suitable for environmental source apportionment studies, but with careful optimization, it can achieve equal precision with the multi-collector ICP-MS for some isotopic ratios, but perhaps not for all. So ratios with lead 204 are less successful. But despite that, it does have potential as perhaps a screening tool where generally more precise isotopic ratios are needed. So given that it's relatively less expensive and the higher throughput at about 16 minutes per sample using this technique, it is now possible to screen large numbers of samples first to get isotopic ratios and then select with the knowledge of those isotopic ratios, the fewer samples that you actually want to do more precise isotopic measurements using other approaches. And if we're going to improve quadrupole ICP-MS further, then we need to look at improving the lead 204 signal. Acknowledgements, I'd just like to thank the whole host of people on these slides, and I've put details of the papers that we've published from this work on that slide. So thank you very much.
Floor from Zoom, people maybe? No? No question at the moment. Okay, maybe later. Well, I have to say that 207, 204 is the ratio that is the most compelling also with the multi-collector. So,
Yes.
all right. Then we switch to Janet Montgomery, University of Durham, diet migration and isotopes. Please.
Afternoon, everybody. Thank you for asking me to come and talk to you today. Today I'm going to have my bioarchaeology hat on rather than specifically sort of chemistry or science. And I was asked to talk on diet migration and isotopes from prehistory to the Viking period. I'm going to concentrate mostly in the first millennium AD, mostly on Vikings, because obviously I can't cover everything in 20 minutes. And really the point I'm trying to get across, and it's been mentioned already this morning, is that, you know, isotopes sound simple. You see people saying, oh, we do isotopes and they solve the problem. Well, they don't always, unfortunately. And as Martin said this morning, you know, we were on a real euphoria with isotopes when we started doing them, and obviously now we're starting to realise there's a lot more nuance in there. We're dealing with humans. Humans do their own thing. They don't always comply with how we would like them to behave, and we have to be careful, really, about how we interpret this data. 20 years ago, today, I'd just had my PhD viva, submitted my PhD, which is a study on using lead and strontium isotopes to look at human migration in Britain. It was the first study in Britain to do this, and there was a couple of problems with it, really. One, there wasn't any other comparative data for me to look at. There was no biosphere data against which to compare the humans I'd looked at. And apart from one study by Doug Price and Gisela Gruppe on bell beakers in Europe, there wasn't any data from the putative homelands of any of the individuals I was looking at. So it was sort of hampered, and from then, obviously, Jane and I we went on to look at producing biosphere maps in order to help interpret this data. But my PhD is actually still being accessed. It's on the ADS website, and it's still being accessed, which is nice. But what sort of came out of that, really, is that we sort of bandied the words about, oh, we use isotopes to find out where people come from. Well, actually, that's not what isotopes do. They're very good for identifying people who are different from other people buried in the cemetery, in the site, in the region. And they're also good for identifying people who are not consistent with the place of burial, which is a different thing to the humans there. But they're not very good for identifying where somebody came from. They tell you where they didn't come from, as has already been said. And they also don't obey national borders, which is a big problem when people are trying to use them certainly in a modern context. And the reason they don't obey national borders is, this is the global oxygen isotope map, they're related to environmental processes, to climate, to geography, to topography. And of course, if you do get an isotope ratio, it's not unique to one place. There is this equifinality in the data whereby an isotope ratio can be found probably all over the world, actually, in some form or other. So we have to be cautious when we interpret this data. The main isotopes that we use to look at migration mobility are things like strontium, lead, oxygen, sulfur, more increasingly. And these relate, as I said, to environmental processes such as geology, pollution, particularly with lead. That's a big problem when the Romans arrive in Britain and essentially mine all this lead and pollute our whole atmosphere. Oxygen's related to climatic precipitation, and sulfur, again, it's a bit of a thorny issue there, but some related to geology, some to environment. Carbon and nitrogen are not so much used to look at migration. And certainly when I started doing my PhD, people who I worked with who were working on stable isotopes, dietary isotopes, carbon and nitrogen, would say, you can't use these to look at migration. But actually now we know a bit more about them and a bit more about how they change over space and time. There are some examples which I shall show you where we can actually use them to identify migrants in cases. Carbon and nitrogen isotopes are based on a food web system, so there is a predator-prey relationship, and as you move up the food web, you get higher carbon and nitrogen isotopes, essentially. We have the C3 terrestrial food web on the left-hand side of this plot, marine food web in the middle, and the C4 over the right-hand side. Now, for us, certainly in Britain, most of northwestern Europe, C4 is not something we have to contend with. There are no main C4 food crops in northwestern Europe that are native. We have the main ones are millet, which was domesticated in China, sorghum, which was domesticated in the Middle East, sugarcane in the Indian subcontinent, and obviously maize in the Americas. So we don't necessarily have to deal with that. There are other things, of course, that affect this. When you start looking at the animals and the plants and things at the bottom of the food chain, these can move your sort of data set around. The different things like manuring and stress can increase the nitrogen. The carbon will fall in dense forest and wetlands. It will be higher in open and dry habitats. There's the main terrestrial marine trajectory. We've got plants down here, meat and milk up at the top. So there's a lot of things going on that can change it. But over time, certainly somewhere like Britain, we have major dietary shifts. So in the Mesolithic, we have people who sit right over here, high marine protein diets, changes completely with the onset of the Neolithic in the Bronze Age and Iron Age, so essentially all throughout prehistory. We get very little people to the right of this line, about sort of minus 19.6 7, 8, it's not precise, but it's around there. And no marine protein consumption, or very little, in Britain. Changes in the Roman period, we have people coming in, obviously, from Europe. We're bringing in different diets, so we do see a shift. Again, in the early medieval period, this falls back, and again, most people at that time were eating terrestrial-based diets. Changes in the high medieval period with the onset of the religious edicts about eating fish, and in the later and post-medieval period, we get a much bigger range of diets. Now, this is useful if you're looking, say, in the Roman period, and this is some data from Hella Eckhart's project, Roman Diaspora Project from York. You can see we have a group of humans in the middle and the herbivores and the pigs down the bottom left. Now, we should get a trophic level shift in carbon of about 1 to 2 per mil between humans and their prey, and about 5 per mil on the nitrogen. And this works fine for this data set. But obviously here in York, we have some individuals with quite different diets. This is an individual with a marine diet, not common, not usual to have this in Britain at the time. And also some individuals here who seem to have been eating C4 foods. Now again, this is no evidence, no archaeological evidence that these were grown in Britain at the time, so it's very likely if people have these in their diet, they've come from somewhere else where they were commonly eaten. This is a very large data set now. I've got this from Sam Leggett's paper predominantly, but it's a collation of a lot of multi-author data sets. So this is looking at dietary variation in Europe, in the early medieval period. And you can see we've got some major sort of shifts here. We've got, on the left-hand side, all the green is England, very heavily terrestrial C3 protein. This trajectory coming out here with the red and the orange is all from Southern Europe, Italy, Croatia, and Eastern Europe as well. And then we've got the purple ones going up there with marine protein, which is Norway. So this becomes interesting when you look at individuals. So this is a study that was done by James Barrett and Mike Richards back in 2004 at West Ness in Orkney. Most of the individuals, all the pictured individuals, had a terrestrial C3 diet, so to the left of that line. There was 2 individuals, 2 male Viking burials, West Ness 11 and 12, who didn't. They had a different diet. They had marine protein in the diet. And the question always then is this marine protein diet at this time explained by status differences? Is it a male-female thing? Is it choice? Did they just like eating fish? Or is it migration? Have they moved to Orkney, where no fish really was being eaten at the time, from somewhere where fish was being eaten? And this is when I got involved, essentially. If you now plot these, we didn't have all this data at the time, of course, but if you now plot those 2 on this plot, you can see that they're within that red circle. They plot quite clearly within the Norwegian trend on the map, which is quite strong evidence, perhaps, that they might have come from Norway. We can then look at strontium and oxygen and add that into the mix. So strontium, the y-axis, oxygen along the bottom. This is a lot of data from the Viking period, from Britain. And you can see the oxygen for Western Britain, which is where the Western Isles and Northern Isles, Western Britain, which is where these 2 Viking individuals from West Ness came from. Orkney is the pink box, essentially. Don't take these 2 literally, they're just really there for visual help to pass this plot out. But you can see the 2 individuals, the 12 and 11, 2 circles, the 2 Viking males, don't fit within what we would expect for Orkney. So they're clearly not indigenous to Orkney. If you put that on for, we put on the oxygen range for Britain, again, they still fall outside that range for Britain. So we're starting to see now that the oxygen isotopes is probably going to say the oxygen's too low. They're probably from somewhere more colder to the north. But if you then start putting on other places where else they might possibly have come from, Iceland, no, they're not consistent with Iceland. Denmark, we can't really discriminate Denmark from England, actually, with strontium or oxygen. Big overlap there, but they're not from Denmark. Antrim, Northern Ireland, not from there either. There's some individuals here, a little cluster, and again, once you start getting more data from the same period, you can start thinking, okay, what do these clusters mean? That cluster, very low for Britain, but still not low enough to actually say conclusively they're not from Britain. These definitely are too low on the oxygen scale for Britain, and that includes the 2 from West Ness. And these sort of very low oxygen isotopes, the higher strontium isotopes. Really, you're looking somewhere, Greenland, Newfoundland, the Baltic Shield, most likely. The other thing we can do with isotopes is lead. And lead is interesting because it changes over time. So throughout prehistory, right up until the Romans arrive, we have very low levels of lead in humans. This is human tooth enamel from childhood, very low levels of lead. Irrespective when metallurgy arrives, we still have very low levels of lead in humans. That starts to rise in the Roman period, and then we get variable but increasing levels in the post-Roman period. And if I put on the sort of 18th, 19th century on here, that would just go off the top of the chart, essentially. So if we combine that evidence for how much lead people were exposed to with the isotope ratios, this is very similar to the plant data that Liz was actually showing earlier, is that we get what we call cultural focusing in that. Before the Romans arrive, we have very variable isotope ratios in the human population, but very low levels of lead. So essentially, most people are below about 0.6 ppm. After the Romans arrive, we get this cultural focusing where the amount of lead in their teeth goes up and the isotope ratio becomes focused on the English, essentially English and Welsh ore lead. So we have this ore lead values, and almost everybody after the Roman period essentially sits within that purple box on this plot. And then we have all these individuals along the bottom. So these are all prehistoric individuals, and also almost all the Viking individuals that we have buried in England. They all have extremely low levels of lead, variable lead isotope ratios, but virtually none of them come above 0.6, which suggests that they've come from somewhere that at the time was an unpolluted environment, possibly with no influence of the Romans ever arriving, which you could class Scandinavia as that. And it sort of helps to, once you start layering up all this evidence, the identification of a homeland becomes much more robust. And if you just go back to that Roman data from York, these individuals here that all have C4 millet in their diet, none of them have English ore lead values. They all have young lead, Mesozoic lead, which suggests they've come from Eastern Europe or Southern Europe. And Mark stole my thunder on this, but this was a study that I did with Rui Martiano and Dan Bradley at York. I'd worked at Driffield Terrace since about 2003, but they came back to do some whole genome sequencing on some of the individuals from York, from this Roman site and other Roman sites. But the individuals they took for the DNA came from Driffield Terrace, which was an interesting cemetery where it was almost entirely adult males, and about 80% of them had been decapitated, and the skulls had been placed in all odd places in the grave, between the knees, under the arm, swapped between individuals. And essentially, the red samples on here are the ones that we did the DNA on. This is sort of York. That's where everybody who would be indigenous to York would sit. And then we have this individual down here, 3 Driffield 26, which had a very, very low strontium value, which suggested it's going to either be basalt or possibly limestone, but also a very, very high oxygen isotope ratio. I was very worried about this data when I got it. I sent that sample back to the lab 3 times, and it came back exactly the same each time. So I went to the meeting thinking, I hope this is right, but this individual certainly doesn't look like he's from Britain. And of course, as Mark said, the genetics of this, the genetic ancestry of all the individuals that they looked at was over here in the sort of northwest Europe part of the plot. But this one individual, this is the one with a very high oxygen isotope ratios, was not. He'd come from, his genetic ancestry was in essentially Palestine, Jordan, around that area of the Middle East. So these combine, we don't do enough of this, there's more happening now, but when you combine these 2 lines of evidence, the DNA can tell you the genetic ancestry, but it can't tell really when that person moved, whether it was him or whether it was his ancestors. The isotopes only pick up that generation that moved, so the moving generation. So combined together, it tells you, 1, this individual moved, and 2, that where they'd come from in Europe. So they work very well together. Recent developments, we've started with the carbon and nitrogen isotopes now. We're doing much more intensive sampling, microsampling, where we essentially split up the teeth, which form sequentially, to produce life history profiles. And we're seeing that the carbon and nitrogen ratios in humans change over their lifetime quite a lot. So when we do this with, these are two examples, two Viking burials, one from the Ardnamurchan boat burial, which is in Western Scotland, and one from the Blue Lady, which was for an Icelandic burial. And you can see these are the carbon and nitrogen isotope ratios. The green zone would indicate terrestrial diet. So you can see they're quite different. These individuals have had different experiences of diet during their childhood. For the Blue Lady, the strontium in her tooth enamel not consistent with Iceland, where she was buried. The oxygen is not really consistent with Scandinavia, it's too high. So it seems that when she was eating the terrestrial diet, she wasn't living in Iceland, possibly in Britain or Ireland. And then later on in her life, you can see the isotope ratios change and she starts consuming marine diet, which was very prevalent on Iceland at the time, but not in Britain and Ireland. Another thing we've done, which is not isotopes, but I just wanted to show you this quickly before I finish. This is something we've published recently. It was in the RCS Advances journal, and we've managed to extract peptides, which are residual peptides in tooth enamel. They're not supposed to be there, but they're essentially peptides from the amelogenin protein, which is the tooth enamel forming protein. And my colleague Nick Stewart found that there was a dimorphic sequence in these amelogenin, with the amelogenin that was secreted from the Y chromosome and the amelogenin that was secreted from the X. So what we can do with that, when we measure it, we can identify sex of the individual from a very, very minor leach of the tooth enamel surface. It's virtually non-destructive. It works when ancient DNA has failed because the enamel is much more robust in a lot of burial conditions. It's a lot cheaper than DNA analysis. It only needs enamel to survive to ID the sex. It works with humans of any age at death because you only produce amelogenin when your tooth enamel is forming. Once that finishes at around the age of 12, you don't produce it anymore. So it's also very difficult to contaminate. So we went back to some of these Vikings that we'd looked at earlier. This is the Ardnamurchan Viking boat burial from Scotland. It looks great on that drawing. However, that was all that was left of that burial, two very poorly preserved teeth. So there was no way you could sex that. DNA would not work. We managed to get a really nice dietary isotope profile out of him, but we couldn't estimate sex either osteologically or with DNA. But we managed to sex the enamel on that one tooth, and it came back male. We probably could have guessed that. But the other way, the other instance when this is really useful is for infants and children. Again, we can't sex these osteologically by any reliable method, but again, trying to sex all the children we want to look at with DNA is very costly and time-consuming. So I went back to a study. I did this for my PhD, and this is another example, really, of things moving on, new techniques coming on. We can go back, we can reassess, and do some more work. So in this cemetery, this is a North family cemetery at Neep on the Isle of Lewis, up in Scotland. And there was three children buried in this cemetery. There's a 6-year-old, 6 to 9-month-year-old, and a neonate. So we managed to sex all three of these. They were all little boys. This is just something that we wouldn't have been able to do otherwise. So this now, when we're doing things like dietary isotopes and the incremental dentine, well, on children, for example, we can sex them. So we can now look at the difference between boys and girls, which we really just never used to be able to do before. So that's me finished. Just to sum up, we've had some major advances really in how we use and understand the isotope data. We're doing a lot of work obviously on domestic animals, which we didn't start doing in the beginning, and using those to inform us about human behaviour. We've got lots of comparative biosphere maps now, and obviously a lot more bigger data sets that we can use to look, but we always need to remember that the data is only as good, and this has been mentioned already, as the metadata about that data. Where was the site? What period was it? What type of site was it? And how do we, we have to bring in the archaeology and the archaeological context in order to interpret that. For me, some of the best insights that I'm getting now are on not big sweeps across Europe, but individual sites, individual places, and particularly when that's combined with the DNA. So, some of the work that we're doing now, bringing in the sort of family relationships between people at a site and comparing that with the isotope data is showing up some really interesting things. And finally, a lot of this, when I started doing this, obviously it was university research, You couldn't commission it really. It was very much in the research sort of zone. But now a lot of the work I'm doing is coming in from commercial companies, commercial archaeology companies. It's getting written into tenders. So all these big projects like Crossrail and HS2 and big road developments in Hull and Cambridge, all over the place. They're all tendering isotopes into the cost of the project. So that's bringing in some really good, interesting new work. And long may it continue. Thank you very much.
Thank you very much. Wonderful presentation. Is there a compelling question from the floor?
Thank you. Now, I have lots of questions, but I won't subject you to all of them. With your lead data, obviously you are taking a sort of an average of all of the lead data across the Roman period, because there's only one Roman point and there's one 5th, 7th century point on your profile.
Those, no, they're not just 1 point. Those are the median values.
Yeah, median values.
All, yeah.
So what level of data is that? Would it be possible, for example, to show a profile through the Roman period and through the 5th, 7th century to show when it's actually having an impact?
Yes, you're right. I mean, the resolution's not so good. I've just got a cemetery at the moment that we're looking at Yapham Lane in Yorkshire, which is an Iron Age early Roman cemetery, and the archaeologists dated those burials based on the grave goods and the grave type. We haven't got the radiocarbon dates back yet, but I think I can date them based on the lead concentrations in the tooth enamel, because there's some with very, very low levels, and then you can see them rising. So yeah, we need to just do more, really. There's not a lot of people measuring lead concentrations in humans, though, is there?
No, and it's...
I mean, I try and do it in all the ones I get in. I'm
Yeah.
accumulating a lot more data, but that finer resolution, yeah, it would be, you're right, would be absolutely fascinating to see when it actually kicks off.
Yeah, thank you.
Yeah.
Other question? Thank you very much. Thanks for the presentation. Okay, we move to Julian Henderson, University of Nottingham. Neodymium, strontium, and boron isotopes in ancient glasses. New information about raw materials used in provenance. Julian?
So, yes. Thank you. Yeah. Okay, good afternoon. Great pleasure to be here. Congratulations to the organisers. I think this is a great day, which is undoubtedly going to lead to lots of possible future opportunities, collaboration and so on. So I'm one of 3 people from Nottingham, no, 4 involved in this conference, Nottingham University that is. What I'm going to do is talk about glass and the application of isotopes to the examination of ancient glass. Inevitably, it's a collaborative endeavour. So since, a long time ago, probably 20 years now, I've been collaborating with Jane, Patrick de Kreiser, Hongzhou Ma, Simon Chenery, and Jens Kroger, and those are just the main collaborators. So the structure of my talk is Islamic glass. I'm going to show you some pretty bits of glass raw materials, to give you a bit of context, the key research questions that most people address when they look at ancient glass, trace element analysis to provide you, again, with context for the isotope analysis. I'll just show you a small selection of slides on the trace element analysis. And really the balance of the talk is about isotopic analysis and then conclusions. So here is some lovely early Islamic glass dating between the 9th and 10th centuries, decorated in all sorts of different ways. Some of this, such as the beautiful Millefiori decorated plaque from Samarra in Iraq, actually partly derives from Roman techniques, and indeed, but on the other hand, pinch decorated vessels are an Islamic innovation. So you've got that interesting continuity, as it were, of techniques running through from the earlier period into the Islamic period, but you've also got innovation.
in terms of decoration. And scratch decoration is one of the key characteristic types of early Islamic glass. Those are found in some of the highest status contexts in China, for example. So they travel the Silk Road right across to northwestern China. Luster decorated wares, you also find that on pottery, but that, believed or not, is a piece of glass. That is also a development of an earlier technique. And not forgetting early Islamic glass beads. The reason I nearly said Viking is that these actually occur a lot in Viking burials, such as on Gotland. The project that I'm working on with Marek Jankowiak and Oxford at the moment looks at the provenance of these beads from Gotlandic burials. Okay, so now onto the raw materials for glass production. What I'm going to do is focus on plant ash glass, and specifically on Islamic glass as well. Of course, there are other types of raw materials that we use for making ancient glass, such as evaporitic sources of flux like natron and borate deposits, but I'm going to focus on plant ash. So quite a few years ago, when it was safe to go to Syria, I went round with a botanical professor and identified and selected plants, which we then determined the strontium isotopes on, and I'm going to show the results of those later. But we also chemically analysed them, trying to determine whether or not they'd be suitable for making glass. Now, there are two key components in plant ash that really are key for the production of glass. One is the sodium carbonate, the thing that fluxes the silica. The other is calcium, which produces a durable glass. So once you've ashed the plants, you combine it with sand or crushed quartz in a furnace. This is the earliest evidence for downdraft glass furnace from Al Raqqa. It was a rescue excavation. It's not a very neat excavation, as you could see, but this is the earliest evidence. There's a downdraft kiln in Central Asia at Samarkand, but this is the only one that I know of that's as early as this. Another example of Islamic innovation under the Abbasids. Okay, so raw glass combining sand and plant ash would have been fused in that furnace to produce large blocks of glass. And it would have occurred in an industrial complex such as this one between the twin cities of Al-Rafika and Al-Raqqa in northern Syria, where I directed the excavations over many years, where we found evidence for both ceramic glazed and unglazed ceramic production and also glass production, combining raw materials in vast quantities. So there must have been communication between the ceramicist and the glass producers. So here are the three key research questions that hover in the back of glass specialists' mind. How widespread was early Islamic glass production? We can apply this to almost any period at all. Can we provide solid proof for the provenance of glass, i.e. where it was made? And thirdly, is there scientific evidence for glass trade? These seem to be the three questions that a lot of glass specialists are obsessed by. Okay, so what I'm going to do now in this fourth section of my talk is talk a bit about some of the results from trace element analysis, which we published in 2016. So we determined trace elements using laser ablation ICP-MS, 97 samples across these sites between Cairo in Egypt and Nishapur in northeastern Iran. And I'm going to come back to some of these sites when I talk about isotopes in particular. Damascus in southern Syria, Al-Raqqa, which I've already mentioned, Beirut in the Lebanon, and certainly Nishapur and Samarra. I'll just give you a quick run through the results of these analyses. So first of all, you can see three zones. All the data seems to fit three zones of characterization using trace elements. The Levant, in other words, the coast, including southern Syria, northern Syria, where Al-Raqqa is located, and the eastern zone combining Iraq and Iran. So we've got Samarra and Ctesiphon and Nishapur, for which we have samples of glass from. Okay, first plot of iron against chromium shows a beautiful distinction, actually I'll go back, distinction between the Levantine glasses and the eastern glasses with the Raqqa glasses, including the furnace glasses, sitting in the middle. Okay, so those are from minerals like chromite in the sand, providing that compositional difference. So that's iron, ppn, milligrams per kilogram, and chromium. Then if we just focus in a bit on the Levant, so this is just Cairo, Raqqa, Beirut, Damascus, and Khirbat al-Minya in Israel, using elemental ratios of cesium against potassium and lithium against potassium, we can see some distinction, certainly between Cairo, Raqqa, and Khirbat al-Minya, but there's a bit of a problem with Beirut and Damascus, as you can see. And I'm going to return to that, particularly in relation to the isotopes that we now have, and show you how relevant isotopes are to this. But the outliers are very interesting, and recent data suggests actually that those are Central Asian glasses appearing in Cairo during the Mamluk Caliphate between the 12th and the 14th centuries. Okay, so if we then look at other elemental ratios in sands, chromium, lanthanum, zirconium, titanium, we can actually see that we have some nice concentrations of data according to the sites on which they are found. Ctesiphon, Samarra, and Siraf, Nishapur up to a point, and very distinct from the Levantine glasses, with northern Syrian glasses being squeezed in between. That's not been identified or found for any other period of the study of ancient glass that I'm aware of. And the fact that Ctesiphon and Samarra are really quite close geographically was a surprise to us, I have to say. So there's clear evidence for the decentralized production of Western Asian, but also Central Asian Islamic glass, according to trace element data. Now, a model for this, Jane talked about models. This is one of the models. We're still working on improving the model, of course. But what we seem to have are three main production zones: the Levant, northern Syria, and the eastern zone, which combines Iran and Iraq. Within those zones, we've got subzones which correlate to cosmopolitan centers where glass was being made. So we got, well, in the east in particular, we've got Samarra, Ctesiphon, and Nishapur, for example. Okay, but also what we seem to have is the first scientific proof of regional glass specialization. These trail-decorated vessels were made in Levant. These colorless cut vessels were made in eastern zone. Art historians have written extensively about these being made in the eastern zone. We've managed to show that scientifically. I will say that Nadine Shibel has also published a great deal on this and supports these interpretations. And thirdly, scratch-decorated vessels, such as those found in China, probably made in northern Syria. And also the evidence for trade between these centers. Although, it has to be said, the majority of the data is associated with those centers. Sorry, I'll rephrase that. The majority of the results appears to be located for those particular centers. We find a degree of recycling for Samarra glass, but it looks as though they're recycling their own glass. So we have a mixing line for Samarra glass, but it looks like that basically they're retaining most of the glass within those centers where the glass is made, and only a small proportion is traded, which is handy if you're trying to provenance glass. So, isotopes. So is there a role for isotopic studies? Neodymium and strontium, for example. Can we refine this picture of production and supply in the early Islamic period? And I will say that all of these results were produced at the British Geological Survey under the auspices of Jane Evans using thermal ion mass spectrometry, as we've heard, the most accurate technique. most expensive, but well worth it. Okay, behind this, we did in 2005, I think it was, when it was safe to go to Syria. Before the civil war broke out, I went on a mad taxi ride around Syria and the Lebanon with my colleague Youssef Bakuda from the University of Damascus, botanist, and we collected sand and plant samples from these zones here. So mainly along the Euphrates Valley, but also in parts of southern Syria and the Lebanon. It's a start. All I can say is we need far more data, and the idea was to determine strontium and neodymium on the plants and the sands, but it does actually help to, when it comes to provenance, it helps obviously to us to be able to exclude the provenance of some things and actually prove provenance for others. So this is something we published quite a while ago, 2009 in Antiquity. So this variations in strontium isotope signatures of plants across parts of Syria. And the main outcome of this was that we have strontium signatures for the limestone steppe in northern Syria, and a contrast the basaltic, if I can say it, basaltic, that's it, area in southern Syria, which is very helpful. And when we come to look at the glasses, we can link these in. So here are all the different locations that we took the samples from. So it's a start. And here are the neodymium isotope results for the sand signatures. And the key thing here is there's a clear distinction between Levantine coastal sand and inland sand deposits here. And we've also plotted the results of the Vrije raw furnace glasses in that same field, and they correlate surprisingly well. Okay, now to come to the results for the glasses. This is neodymium against strontium, as you can see. So what I'll do is try and guide you through it, and I'm going to expand a little bit more on the next slide. Okay, so on this, we've got the values for the neodymium isotope values for inland sands here, and the Levantine coastal sand neodymium values here. Syrian plant ash values for here. Okay. So first of all, in that red square, we have the 9th century Vrije raw furnace glasses and vessel glasses, and some vessel glasses from Damascus showing that those vessels in Damascus were made with Vrije glass. The second area, 11th to 12th century Damascus vessel glass, dating to 9th, 11th and 12th century Raqqa vessel glasses and Beirut vessel glasses. So the key thing here is that the Damascene glasses do form a tight group just there. The third area is raw furnace glass from Tyre that was published by Patrick et al. With contributions by Ian Freestone, for example. They form a relatively tight group here, but also Banias raw furnace glasses and Beirut crucible glass, which shows that the Banias, that particular sample of Banias raw furnace glass was made at Tyre. And similarly, quite possibly, the glass in the crucible in Beirut was also made in Tyre. The fourth area is the rest of the Banias raw furnace glass. So this is a glass working site in Israel, which also forms another relatively tight group. It also includes a raw piece of furnace glass from Raqqa and one crucible fragment from Beirut. And lastly, the big glass shipwreck dating to the late 11th century, the Serçe-Lamani shipwreck that was wrecked off the west coast of Turkey. We managed to get hold of 4 samples. There were 2 tons of raw glass found on the shipwreck, but we managed to get hold of 4 samples, which we hope are representative. But anyway, they form a separate group too. here in the top right of the diagram. So, do isotopes refine the picture established by trace element analysis? Yes. So we got distinctive isotope signatures for primary glass production centres, Al-Raqqa and Tyre. We have isotope signatures of only, as I say, 4 samples taken from the 2 tons of raw glass found in the late 11th century Serch-el-Amani shipwreck. Show they were made in a Levantine primary glass making site, but not at Tyre. So again, as we said earlier, you can sometimes exclude things, but we don't actually know precisely where that Levantine primary glass making site is, of course. Damascus was an important regional centre and an Abbasid capital. The 12th century glass forms a tight isotopic group, suggesting, unsurprisingly, that Damascus was a primary glass making centre. You could also suggest that they result from glass recycling, but we rather prefer the former interpretation. So the raw glass from the secondary glass working centre of Banias forms a distinct group, along with a single raw furnace glass from Al-Raqqa, providing evidence for a third Levantine glass making centre. It has characteristic Levantine sand. Al-Raqqa surprisingly imported raw glass from that centre, only 1 sample, but it still did. It was a massive industrial complex, 2 kilometres in length, but given the connections across the Abbasid Caliphate, it's not always that surprising that you find things being traded around, up to a point. The samples from Beirut, including crucible glass, suggest that the city depended on other glass-making centres. Of course, this is only as good as the data we've got. And this could explain why the trace element data for Beirut is rather mixed. So isotopes have provided a real clarity in distinguishing Damascene and Beirut glasses. Okay, well, I thought I ought to mention boron isotopes at the end. I was far too optimistic when I said I'd talk about boron isotopes. We don't have any new data. All of it seems to have been published by Patrick de Creese's group. These are figures from De Velde et al. Published in 2014. So this is a newish technique, first applied to ancient glasses around 2013. As I said, boron is found in evaporitic deposits and sands, both evaporitic deposits and sands. So it's an important technique for the study of mineral sources, of sodium salts, including natron and borate deposits. There are well-known borate deposits in Turkey, which were probably used to make Byzantine glasses, and Ottoman Iznik glazes. But we do know of others, and there's more work to be done, which we are working on. Anyway, I wouldn't like you to be disappointed by me not mentioning boron isotopes. Okay, conclusions. First of all, trace element combined with neodymium and strontium isotopes both provide important evidence for glass technology, provenance, and trade. In the early Islamic period, these techniques have provided unusually comprehensive evidence for decentralized plant ash glass production in cosmopolitan cities along the Western Asian Silk Roads, even without archaeological evidence for its production. I should have said, but I didn't. We have done, myself and the group in Nottingham, combined with BGS and Patrick's group, have done a lot of other work on a range of other types of glasses, including Bronze Age, Roman, Byzantine, High Medieval periods, with also some very interesting results. But anyway, to carry on. Number 3, neodymium and strontium isotope analysis has provided a much more sensitive means of defining glass provenance in the Levant than trace element analysis. So there's absolutely no doubt it has a role. And of course, it's only as good as our database, as we've heard several times already, and certainly we need to do much more environmental sampling. But I would imagine I need to go back to Syria with a security detail in order to do so, and I'm rather loath to. Boron isotopes provide an important means of investigating especially evaporitic sodium-rich minerals used in glass and some glaze production. And just finally, I thank you. Thanks very much to this range of funders. Thanks a lot.
Thank you, Julian. Any questions about glass isotopes? Please.
Thank you very much. To what extent did the glass production technology developed, say, in Damascus, was exported as a technology westwards, particularly during the period of knowledge development in the West in that early medieval or later medieval period?
Yeah, very interesting question. Well, we do know there are historical texts that actually state, first of all, that the best plant ashes were imported from Aleppo in northern Syria. So that answers your question partially. But it is true to say that the early Venetian glasses were plant ash glasses, and indeed it is built on Islamic glass technology. But obviously, the Venetians developed their technology in the refinement in which they blew their vessels, and also the enameling. But even the enameling is borrowed and based on Islamic technology, particularly the Mamluk enameled vessels, which was a real specialization, and the Ayyubid, so 11th to 14th century. Those enameled vessels, very highly decorated. But I think that one could claim that Venetians certainly refined some aspects of it. I don't think there's any evidence for, as it were, technicians moving from the Islamic world to Venice, but there may be, that I don't know about. Yeah.
I was just thinking of maybe the written transcripts, because there were a lot of materials in Arabic translated into Latin in the Renaissance period.
Yes, fascinating, and similarly, classical texts translated into Arabic during the Abbasid Caliphate under Al-Mamun,
the House of Wisdom.
Yes, indeed. Yeah, some incredible recent translations, in fact, of the technique of luster decoration. But because they're alchemical texts, they're partly secretive, so almost impossible to understand. But anyway, yeah, it's a very interesting area of research. Yeah.
Other questions? Thank you very much, Julian. And we switch to Stephen Merkel, talking about the lead isotopes and modeling for the Viking silvers.
It was Merkel. Yeah. Okay. Great, thank you. Thank you very much for inviting me here. And I will be talking today about my project work with Jane Kershaw. So we're working on an ERC project and we're looking at Viking silver. So I'm really happy to see so many Viking presentations today, especially those pictures from Janet. Okay, so the Viking Age is an age of silver. So the Vikings used silver. There was a lot of silver available. In Scandinavia, though, they don't have mines for silver at this time period. So the silver was coming from coin-using regions in Western Europe and in the Middle East. And the Vikings used it, they collected it, and they used it to make jewelry. They used it as a medium of exchange. And so we have lots and lots of hoards, lots and lots of silver. And so our question is, where is the silver coming from? I mean, we have some coins, but there's a lot of silver that is not in the form of coins, but as jewelry, as large rings. And so we want to know where the silver is coming from. So we all know this story, this part of the Viking expansion to the west. They raided, they settled, they pillaged. And of course, the question is this silver that they raided going back to Scandinavia? Are they using it to make jewelry? what's actually happening here with the metal. But at the same time, there is an expansion eastward. And according to the coins that survive, we see that there's a trickle of silver coming from the Baghdad area, from Iran, up across through Russia into Scandinavia. But the main phase, we have lots and lots, thousands, tens of thousands, you see, coming from Central Asia, around 900, going across into Scandinavia. So our question, our basis question is the Western expansion and the Eastern expansion, which are seen generally as two different phenomena, are they actually connected? And we are exploring this question in our ERC project. So this is Jane Kershaw in Oxford. Me, I'm doing the archaeometallurgy, and Jani, who's in Finland, and he's our numismatist. He studies Islamic coins, which is actually extremely important for us. So we are very ambitious in our project, and we are about 3 years into it. And so we have about 2 years left, and we're still in the data collection phase. So this is definitely preliminary. So in this talk, I'm going to talk about our reference data, because this is extremely important. How do we interpret the data? We need the reference data. And then I'll talk about modeling. So I'm going to talk about the modeling of Islamic silver and why that's absolutely necessary in our case. I'm going to compare the model with Gotland and Hedeby. And finally, I'm going to take this all the way to England to look at some hoards here too. Okay, so for the reference data sets, we start with lead, because lead and silver have a very special relationship. They're often together in ore, but you also can use lead to refine silver. And naturally, if you refine it, you want to clean all the trace elements, all the copper out of it. You can add lead to it. And then if you do lead isotope analysis, you're tracking actually the lead that was used to couple it. So we started with a database of lead finds from Scandinavia to characterize what kind of lead is available in Northern Europe. And what we can say about this already is that it all comes from Western Europe, so North and Western Europe. So we have lead coming from England, from France, from Germany, but there's nothing coming from the Middle East. It's all sort of local in a Northern European sense. Okay, and so we have Western sources of silver. We don't know exactly where all the silver is coming from. We have coin analyses from France, and now we have new coin analyses from England. And the good thing is that most of the coins from France fit with Mel, a mine in France. And most of the coins in England also either fit with Mel or with British lead. So this is kind of a unit here that's self-contained in a way. But what we didn't have is the Islamic part of it. So the dirhams, the Umayyad and Abbasid dirhams. We have, before our study, there were about 30 analyses published. And so we had to we quadrupled the amount of data. We did a lot of analyses on Islamic coins to fill in this reference data set here. But what we found is that Islamic silver is incredibly diverse. So we have ore deposits all the way from Morocco to the Tian Shan and Central Asia. So it's incredibly diverse. And how can we use Islamic coins to find out about recycling? So that leads to the challenge, but also to our model. So the thing is, coins are very small. So here the dirhams are typically 3 grams, but what happens is that a lot of the Viking artifacts are large. So you might even need 100 coins to make a neck ring. And so there must be a lot of recycling, of homogenization. So you have a diverse small amount of these coins and you homogenize them into a large ingot. So this is the idea that we had, that they are recycling dirhams on such a scale that they're homogenizing it, and hence our model. So Yes, you see a lot of numbers. The numbers aren't exactly important, but the important thing is we have Durham hoards in Gotland that survive. So we have Durham hoards and we can date them with the TPQs. So they've been studied. We know exactly what kind of coins are in these hoards and how many of them. And so what we can do now with our data set, there's 160 analyses, is we can actually match the coins 1-to-1 in the hoards to get the right proportion, to get the right geographic area, to get the right chronology. And a lot of these hoards, we can actually match up to 20%, or up to 70% with the coin that we analyzed by mint and year plus minus five years. And the lowest amount is about 50%, but basically all the coins we can actually model. We can fit into either chronological or geographic groups now that we know the patterns of where the silver is coming from and when. And so we're able now to create a homogenization. So if you have an entire Durham hoard, you melt it into one object. This is the composition that you would get. And we can do that now with isotopes and also with elemental compositions. So with the gold and bismuth, these are the ranges that we would expect for recycled Islamic silver. Okay, so the reference data here now compared together. So we have the European lead, the lead artifacts from Scandinavia. You see that there in the blue. You see Mel. And so the silver from Western Europe fits within Mel and with the lead from, most likely from England, from France, and from Germany. Okay, and so the Durham models. Here you can see there's a shift in isotope ratios over time. I put here plus minus a standard error just to show a little bit about the diversity or what the variation you would expect here is. So the early Gotlandic hoards form a small group, and it shifts up over time into the later 9th century because there are new mines that have been discovered, and these have different isotope ratios, and the proportion of this kind of silver is higher in the later phase. So we can actually separate early 9th century from late 9th century Islamic silver. Okay, so how does this compare to the actual artifacts from Scandinavia? So first we go to Gotland. Gotland is the silver center of Scandinavia. For some reason, silver from all over just ends up there. I don't know why, but somebody knows why, I'm sure. Okay, but there's lots and lots of silver on Gotland, especially early silver. And here is an example of a hoard that we also looked at. Here it had some coins with it, but most of the silver is, as you see, as rings, as ingots, so not coins. So we analyzed some of these hoards from Gotland, which we know come from the 9th century. And so here is Melanie Schmidt and Gunnar Andersson, who were in Stockholm here. And we analyzed these with in situ laser ablation. We did both trace element analysis and lead isotope analysis using this method. Here's laser, here's analysis of a standard, so that's why we make so many holes right next to each other. We don't do that on artifacts. Okay, so the material that we analyzed from Gotland plots this way here. And you see it has larger error bars because we did it by nanosecond laser ablation. But the interesting thing is that all the artifacts, except for one, all the artifacts fit with this early Islamic signature, so pre-850 if we go by the Durham hoard models. Now, if we go a little bit further in time, this is Hedeby, and this is where I did my PhD research. And this is old data, but we didn't have the Durham models at that time. We just have them now. So I can go back and reinterpret this kind of coin, which was made at Hedeby and definitely made of recycled silver because there's no silver available here. And what we can see is that at the year 900, they're using all of the Islamic silver here. There's one coin that fits with Mel. We weren't able to get elemental data from that, so we can't tell if it's coupled with Mel lead or if it's actually Carolingian silver that has been reformed into a coin. But we see here that the model seems to work. It really matches and lines up perfectly with what we find archaeologically. Okay, so the last part here is about England. We analyzed this hoard with Jane Evans, who's here, at BGS. So she did the lead isotope analysis. This is a hoard in Yorkshire, beginning of the 10th century. And it has no coins in it, but it can be dated through stylistic features in some of the finds. So it's about 900. And we were able to actually take little samples for the lead isotope analysis. So it hardly broke through the surface, but that was still enough for the lead isotope analysis. Okay, and so we find basically the same phenomenon here, except, of course, there's more Western European silver, or at least lead coming from Western Europe in the silver. We see Mel, but we see also this jump that goes up following the Islamic silver. And I mean, this is very, very interesting because we always thought that the Vikings were in England to take silver and not that they're bringing silver from Scandinavia here. And so we've been actually analyzing a few hoards now. We did this very, very early on in the project. We've analyzed a few more hoards, and we're finding, of course, different proportions of Western and Eastern silver. So we've analyzed a hoard, the West Coast Cumbria hoard, and that looks very similar to this. We have a lot of Islamic silver in that. But there's other hoards that are mostly Anglo-Saxon or Carolingian type silver, like the Galloway hoard has mostly silver that we can connect with the Anglo-Saxons. So there's a lot of differences, and each hoard has its own character and its own story. As I said, we're still in the data collection phase, and so we're still trying to see the big picture, but we're finding some really interesting results here and turning what we thought on its head, particularly here, that we have this silver. Okay, so the conclusions here are findings. So with the large-scale analysis of Islamic dirhams and the hoard data that we have from Gotland, for example, we're able to have a time-resolved model of recycling, so we can see different phases of Islamic silver. And I didn't show you, we can actually go earlier and we can actually go later to then this time period. So we can actually see 2 centuries of recycling of Islamic silver if we wanted to. This fingerprint enables us to compare with the Gotlandic material with hoards in Scandinavia, with England. We can now identify Islamic silver in a way that we couldn't up until now. And what we're also able to see in this data is that a lot of this early Viking material in Gotland, for example, the big neck rings, the arm rings, this silver is Islamic. And even though the coins don't survive, we can still see the signal in the objects themselves. So we can go back and we can reveal parts of the past that we couldn't see up until now. And so we can rethink this connection to the East, that even though we don't have a lot of dirhams, we have a lot of silver. And so this raises this connection. Are the two movements, East and West, connected? And that this flow of silver that's coming in from the East actually encourages the Vikings to go west and to take over areas, to settle areas, and that it's not exactly the fact that they're poor and they need money and are raiding Western Europe for that reason. So, so there's a lot of new things coming out here, and thank you guys very much for your attention. I would like to thank the collaborators that we've worked with and the organizers and the ERC. So thank you very much, and here are some of the latest publications that we put together. So, thank you.
Thank you very much, Stephen. Very interesting, this back and forth of silver. Any questions from the floor?
Good afternoon. My name's Stuart Pearce on behalf of Royal Archaeology. Just a question in relation to a coin that was found as part of our investigations in a search of the Battle of Brunanburh. There was, I don't know if you're aware that there was a Durham found as part of our research and metal detecting investigations, and that was minted in Baghdad between 776 and 777 AD. And I just wondered if you plan, obviously that's registered with the Portable Antiquity Scheme, and I wondered if you've got any plans to examine that in some way to see if there's any connection with your research that might add extra value in terms of you know, where it's come from, etc., etc. Obviously, it was minted in Baghdad. Yeah. And secondly, I'm curious. It's a bit of a chicken and the egg syndrome, really. Is it? Do you think the ingots were from melted down dirhams, or vice versa? In other words, the ingots have originated from the Far East and they've been used subsequently to create silver blanks and therefore struck into dirhams, or that they're, my thoughts are they're possibly that the ingots are possibly melted down dirhams. I just wondered what your thoughts were on that.
Okay, yes, I do remember the finding of this dirham, and that my colleague Jane was in contact and was informed and about that dirham. We have actually quite a few analyses of dirhams from that time period from Baghdad. So we have about 40, if not more, analyses of Baghdad dirhams, and they're very, very interesting, especially the fact that in the year 773, we see a whole new shift of isotope ratios. They discover new mines, and these mines look like they're coming from the Taurus and the Taurus Mountains. And this is revolutionary, I mean, for the period. And that's actually what the shift in the isotope ratios is the proportion of dirhams from Baghdad, particularly with this new kind of isotope signature. So the analysis of these coins is really important for our research. Okay, about the question of the ingots, there's no real evidence at the time that in the Islamic world that they're producing ingots and trading in ingots. The earliest hoards that we have that we know of from, for example, in the Caucasus Mountains are all dirhams. They're all just coins. And at some point, they turn into ingots. They turn into jewelry objects. And we think that there's a lot of recycling in Russia already to make large Permian rings that can be 400 grams. That's a lot of metal. But I mean, in Scandinavia itself, at this time period, they weren't using coins. They used silver in large transactions. They used it as jewelry, so they didn't really have a use for the coins. And it's only later on in the 10th century that they start using coins as exchange items and in small proportions for buying little things. And so then you have a lot more coins that survive. So
it's more likely to be melted down coins.
I think it's
as an origin.
Melted down
There's a
coins.
supplementary question, which I forgot to ask before. Do you think the presence of any of these dirhams, whether it be in the Wirral or anywhere else, do you think that's indicative of settlement, trade, or something like a battle? Do you have any personal thoughts on that?
Oh,
I'm curious.
Well, I mean, I think the Vikings had coins with them. So if they were in settlements, they were using them for trading. I mean, at that time, sort of late 9th century, beginning of the 10th century, they're using them in transactions, using them as raw materials. But I would suspect that dirhams in England have something to do with the Vikings and Scandinavians. So.
Thank you.
Very much. Any other questions from the floor or from remote? If not, I think we go for a coffee break because we are a little bit late. Then we reconvene for the last session.
Okay,
Thank you very much again.
you're welcome.
Very smart.
Are we ready for our final session? We are on a schedule for the 3 final talks and then a more general discussion about what we've heard today. Gilberto, please, will you commence?
Should I? All right, set. Okay, so I'm talking about lead isotopes applied to metals, of course. So that's the topic we selected. Just to set the frame a little bit. This is from Renfrew. If you follow more or less, you know, this of course, this is revised from one of the earliest versions, and this was already pointing to maybe 3 spots, you know, multiple starting of metallurgy. That was not the case in the first edition. Actually, very interesting, in the last edition, they eliminated these plots. But anyway, Italy is between 2,500 and 3,000. And I suppose that this is related to the actual smelting and use of the ores, because metals, of course, were you know, around much before for the use. And if you look at this very recent Upland book, is basically following exactly the same pattern and picking up again. We are, you know, around 2,500 or so. And if you go to Wikipedia, again, we are a little bit before 3,000, 3,500. Already we have 1,000 years of starting of metallurgy in Italy, more or less, just in the current, you know, plots. And I found this very, very interesting. I like it a lot. Actually, this is talking about musical instruments. And it's in the Journal of Psychology, and it's relating the starting of metallurgy with the, you know, building of instruments. I think it's a very, very interesting study. But what it was interesting to me is that on the contrary of the previous plots, is already pointing to the metals coming into 2 different directions in Italy. See, one through the Balkans, the other one through the Mediterranean. I'll get back to that. And of course, you know, Pigots and Benjamin, I mean, they already, this is putting forward the unilateral, you know, movement of metals. They point to one source alone, and again, Italy is around, you know, 4,000 or something like that. So we have widely different ideas on when metallurgy started in Italy and how it started, and I get back to that. For a long time, they were relying the Stuttgart project, and before that, Otto Witter. They started to look at the chemical analysis, and the Germans did a huge projects all around Europe, trying to relate the sources of the metal, you know, through chemical classes, basically, trace elements. It was very important to group and cluster, you know, different kind of compositional classes of metals, but not really to relate them to the sources. And of course, the you know, radioactive elements, especially the uranium, thorium, into lead, are the one that geologists have been using for a long time in order to relate the age of rocks and formation of you know, the minerals. And these are the models that we apply in order to interpret these data and actually relate them into this. I'm not going into the isochrones, but you know, is what we see when we actually look at the ores and try to interpret the different deposits. Each deposit has an age, and this is the age which is we are relating to the objects, basically. There is no evidence that you can change the isotopic composition when you're doing smelting and reusing and recycling of metals. So one of the major points I want to make is that when you obtain and measure data from the ores, you need to interpret the geological background of the rocks and interpret exactly what you're looking at. And this should be done in geological terms to these isochrones that you can see very well from the deposits, or mixing lines and subsequent you know, processing through metamorphism and others. So you have to know the data you are comparing. That's very, very important. This is an example from the Oxalid. You know, most of the Aegean data were done by the Gales. And you can see, well, this is actually something that we never published. These are the bronzes, the Riace bronzes. And you can see that actually they are from Lorion, okay, of all the data. You can really see very clearly where the bronze is coming from. When there is overlapping fields, this is two-dimensional, but of course we will look into 3 dimensions, then you can still see that the trend, this is Sardinia, for example, and the Alps, they have different trends. So if you have one data, it's very hard to pinpoint, but if you have a series of data, it's much better, you know, to compare them to the geological models and the isochrones. And finally, I mean, I think that most of the people is now plotting into the 204. That is actually, you know, following the isochrones and the geological reasonings. I don't think the 206 is plotting into the ratios of 206, you know, is as telling as the geological diagrams. Why did we start to look at these databases? Because we worked on the Iceman X a long time ago. Actually, we did some neutron data for the manufacturing of the X. And at that time, they asked, do you want to sample and look at the provenance? And I said, no, because I don't have a database to compare to. It's absolutely useless to, you know, analyze an even important artifact if you don't have, you know, the mean of interpreting that. Then we spent a long time trying to put together, as most of the people here, and the database, starting from the Oxalid, of course, that is the core of all the lead isotopes that we are using, and then adding all the Alps that were completely missing from all of the databases. It took us, you know, almost 10 years and a few dead PhD students, but we are confident that now we have all the very careful data of all the occurrences, even small occurrences in the Alps. So we do have the alpine data to be compared to, you know, of course, we, as all of the others, we put together all the literature, we are increasing and completed several of the areas like Cyprus. We have a lot of data from Cyprus that have not been published yet. Actually, you know, you measure them and we have the data. Sardinia was completed and all sorts of things. We worked a lot with Ignacio Montero to complete the Iberia that has now been published. So we do have, you know, a fair amount of data to compare to. And finally, we published also some part of the data of the Alps that are very helpful. And of course, we are using them in 3 dimensions, and we can certainly very carefully, you know, identify the major ore fields in Italy. The Western Alps are not shown here, but you know, the data are there. And of course, the different districts in the southern Eastern Alps, the Ligurian and the Tuscanian ore fields. So finally, we had the database, and because everybody was believing that the X of the Iceman was alpine, we sampled from you know, a defect that is present in the thing, and we plotted it, and of course was from Tuscany, and that was, you know, a big you know, shock for most of the people, but I think this was very much confirmed. Not just from the isotopic data, but also we were very lucky. We were looking at a, you know, a smelting site exactly of the same age in Tuscany, and they fit very well all the data and the composition and making the inclusions and everything. It's the site of San Carlo, which is actually very important, and pushing back a little bit the use of the smelting of Tuscanian ores. This is the site. It was actually a rescue operation, but there you do have all the chain operation from the crucibles. You know, the slags and droplets of the metal and everything. Databases. We are at the point where each group working as its own database. And in this, for example, publication, they quote a number of databases, and unfortunately, many of these sites are not in operation. They're certainly not maintained, and some of them are not even databases. So it's a very funny situation. Okay, if actually the Alpine is not even mentioned. Okay, and that was published at that time. So it's a very confused, situation, and we should put an end to that. And the literature is full of partial data. Okay, like if most of the Austrian and German literature is ending at the boundary, not mentioning some of the southern Alpine that actually turned out to be very important. Even Sophia Stokes-Gale, I mean, when they published the first set of data for the Scandinavian, they were not using the Alpine data that turned to be actually extremely important because 90% of the objects that they analyzed were from the Alps. They didn't identify them in the first paper. And it is just when they came to us with the data and said, listen, we cannot identify the sources, that we actually compared with our database and find that, yes, it's from Alpine ores. So I think that we should be very careful in interpreting the data. The data are very powerful, extremely powerful, but we have to know, what is in the database, how to interpret the data. That's the final message. Because if we put together all the data existing in literature, like we mentioned Killick, and we have really thousands and thousands of data from all over the world, and if we put them together just in the Mediterranean European area, we have a mess of data. I mean, any objects, if you just take bluntly, the database and compare, you find different solutions that go from Iberia to Morocco and Iran. I mean, you have to know why and how to interpret the database somehow. Anyway, so this we are pretty confident that in the central Mediterranean area we have a grasp on when and how most of the ores were used, and also we can identify very clearly one ore field from the next one. For example, the Alps, we have two major areas. We know which one went in operation before or after. We know if there are mixing lines between the two. And if there are overlapping fields, we look at the chemical elements, and we are also discriminating the chemistry on the top of the lead isotopes. And so usually it's turning out to be very nicely. This is an example, for example, of the early Bronze Age objects. This, again, has never been published. But you see that most of the objects, apart a couple of them coming from the Balkans, I mean, they are really fitting with the Alpine ores for the early Bronze Age. So, you can also discriminate if the Trentino mines or the Valsugana mines were in operation at different times. The data are so, let's say, reasoned that if you take these legs, of course, are not traveling much. They are all from the same area. But looking at every single mine and every single lagging place, the smelting places, there is a neat change in the metallurgy in the Eastern Alps. In the Chalcolithic times, they are all at the bottom of the valley, near the settlements, near the river. And in the Bronze Age, they are all up, above 1,000 meters, with a completely different way of operation. So this is the settlements that were where we have, you revised, most of these occurrences recently. We can tell exactly each site where they were getting the ores. And we see that all along the Adige rivers, they were coming from Calceranica, and whereas Monterey de Cerso were actually exploiting. So maybe there is some hint of control of the areas, okay? Some places were using some mines, some other places were using the other mines. And some were actually mixing together. And you can see clearly the mixing of the ores from one mine to the other. So it's getting a little bit into the, societal and economical interpretation of the smelting, not just the technical one. I think I skipped this Rinaldone one. The only thing is that Of course, the Rinaldone is the culture of the second part of the fourth millennium, and it's mostly from Tuscany, as it should be. But we were very surprised that we're actually using some other ores, especially from France and the Western Alps. So there was a sort of Tyrrhenian, what I call the Tyrrhenian circuit at that time, which is very, very interesting, I think. I'll show you some new data. That is, again, not only they are not published, but they're not even being discussed properly with Gunther Kaufmann, which is the archaeologist that actually is paying for that. Because of the, Tuscanian copper going to the Alps and at the Iceman, and then they found another in Zug, another axe, made of Tuscanian copper. We wanted to see the extent of the use of Tuscanian copper. So we've been analyzing in the last 3 or 4 years most of the important prehistoric axes, Neolithic axes in Italy. And these are just some of those that have been analyzed all around from central Italy, northern Italy. There are actually many, many others. And just to put them into context, okay, because most of these axes are actually stray finds, and there are very few that are well dated. So what we did is actually not make any assumption on the dating. We got the analysis, and now I am interpreting them on the basis of the provenance, okay, and firing back the questions to the archaeologist. So what I plotted first is the coeval, objects that are in the literature, and you can see that. I'm sorry that you don't see that very well, but if I plot all the axes from the Balkans published by the Germans, 3 minutes, I'll finish quickly. The axes from the Balkans and the one from the Rinaldone, you see the Tuscanian, and most of the objects from the Mont Sea and the Rive de Bush that have been published and the Balkans are actually fitting very well most of the Bulgarian ores and a few of the Serbian ones. You have the stray Tyrrhenian, what I call Tyrrhenian from the Rinaldone. And there is this very strange, the Singen copper, okay, that is being not interpreted very well, but it's a very interesting one, and I'll show. And you see exactly the same thing, if you plot in 208. Again, a bunch of materials from the Balkans. The Singen copper, this is not fitting the Alps or the Balkans very well. Tuscanian one and a few stray ones, the Serbian and the French ones. If I plot the ols, and again, ols are very, Mark likes them very well. And again, if I plot all the ols that are, late Neolithic, very early Chalcolithic, they fit the Balkanic field very well. So all of them. And if I plot the ones that are in the 3rd millennium, they fit the Alpine. And they also already tell very much that in the 4th millennium, Balkanic copper was coming to Italy, and the Alps were opened up in the 3rd millennium. Okay? That is very clear. Now, starting from that, of course, Balkanic means mostly Bulgaria, a little bit of Romania, and a little bit of Serbia. Okay? Now, this is the 208 tells exactly the same thing. You can even see much better the geological trends, okay, that we actually use. Instead of one object, if you have several, they are aligned on the isochrones of or the mixing lines of the ores. And this is much more powerful, of course. Now, if I plot this is not published yet, so please don't take notes or something like that. But anyway, if I plot all the axes, there are 3 major fields which are very clear: Tuscany, Balkans, and the Alps. Okay, these are no doubts in interpretation. And then there are a couple of what I think still very early axes, and from the Balkans, one from Romania and one from Serbia. But this we can talk about, especially the Campagna one. I think it's very, very interesting. But then there are 2 groups that are a little bit more problematic in interpretation. One is a group of axes that is fitting perfectly the zinc and copper. And the other one is, of doubtful interpretation. It can be Balkan, it can be a mixture of the two. Okay, we can think about that. So now what I'm doing is that this is 208 and I can interpret them extremely well in the other way. So what I do is that of all these axes, actually, there are only a few which are well dated. This is the Remedello, it's the Celetari Passeri, of course, the Iceman and the Zug, okay? And that's it, more or less. A little bit, we can talk about this Piglonakov, again, the date can be shifted a little bit. But based on the interpretation, which I think I'm firmly convinced of, I can tell that there are a number of Balkan provenances, and these are very early. I think they are all end of Neolithic or early Chalcolithic. Then there is a period in this, the Rinaldone period, 3500, and it's ending again with Remedello II, which means that they go well into the third millennium, 2800 before Christ. And there is a Tuscan period, heavy use of Tuscany, right? And then the Alps start, and this is the bell beaker, okay? So I think we have a very good grasp of the movement of the metal. We start, end of Neolithic and early Chalcolithic with the Balkans that spreads all over the place. Virtually all copper we have is from the Balkans. Then there is a period of heavy Tuscan use, and this is compared with the Rinaldone, Remedello, the full Remedello, Celetari Passeri, and then I think it's spreading also to the Gaudio, but there are no evidence or measurements of that. And then finally, we do have the bell beaker, Campaniforme, that is actually starting, and the Alps are starting, and there is copper for everybody at that point. Okay? I think it's quite clear. There's very, very mixed. I think this interpretation will pose a lot of problems with the archaeologists, because some of the axes have been interpreted from a purely typological basis, and you will have to shift the chronology by about 1,000 years. Thank you very much.
I was just about to grab Gilberto. Time for one question. If there is one possibly online. Nothing online. No questions for the moment. Oh, then you've usefully used up all your time. Thank you very much, Gilberto. So we can move to the next speaker, Daniel, quite quickly. Tin isotopes.
All right. Thank you, Patrick. And first of all, thank you to the organizers for inviting me to this one-day conference and giving me the possibility to talk about the application of stable isotopes in archaeometallurgical research with special reference to tin isotopes. Okay, we have been working on tin isotopes and stable isotopes, especially on tin isotopes, for almost 9 years now. And I started working on isotopes and tin isotopes during our ERC project, our Bronze Age tin ERC project, which lasted from 2013 to 2018. This project was, we did it in Mannheim in collaboration with the University of Heidelberg. And the primary aim of this project was to find out whether tin isotope analysis is a helpful tool for tin provenancing. And what we did a lot of systematic investigation on tin ores and artifacts, characterizing them with tin isotope analysis. We analyzed almost hundreds, 500 of Eurasian tin ores, Eurasian bronze artifacts, and tin artifacts. We carried out experiments with which we wanted to find out what happens to tin isotopes during the pyrometallurgical processing of tin ores. And we also included lead isotopes, copper isotopes, and trace elements into this research, all with the aim to find out more about tin provenance and exploitation in the Bronze Age, and also the spread of tin and bronze metallurgy in the 3rd and the 2nd millennia BC. At the end of the project, it was in fact possible to give a clear answer on this question: is it possible to pinpoint tin provenance by means of tin isotope analysis? And this answer is clearly no, it isn't. So this sounds like a very frustrating result after such a long-lasting project. But besides this big no, there's also a big but. We can still use tin isotopes for narrowing down the tin origin. And here in the next slide, I show you tin isotope data of European tin ores. And what we see clearly in this diagram is we have a strong data overlap between the different tin provinces that we analyze, or from which we cassitarites have analyzed. So there cannot be positive allocation of the tin isotope composition to a potential ore. But as I said, we can use the data for the exclusion of possible sources. And here data, tin isotope data from a recent study of bronzes from Sardinia. Here you, the blue bar shows the variation of the tin isotopes in the bronzes. And when we compare it with the local ores of Sardinia, we see there is a mismatch between the ores and the Sardinian bronzes. And though this is very clear indication that the local sources of cassiterite have not been used, so the tin for these bronzes must have been imported, must have come from abroad. Okay, data overlap, we all know, is a general problem of isotope data and even chemical composition, so there's never the possibility for an unambiguous answer to the question for provenance. This is more pronounced for stable isotopes like tin, copper, and silver than for radiogenic ones like lead or osmium. And that's why we tried to find an alternative application of the stable isotopes, especially of tin isotopes, for getting more information out of the material that we analyzed, which is beyond the mere question of provenance. So the alternative was simply combining different analytical proxies, different isotope systems with a chemical composition, with technological and archaeological information. So this is what I would like to call the holistic approach. Concerning tin isotopes, we are faced with another problem, which comes at the expense of data comparability. So tin has 10 stable isotopes. So in principle, there's a large variety of isotopes ratios possible that we can use. Our group tends to use the 124 to 120 isotope ratios. Other groups used other isotope ratios. Another problem is that there's still no international certified reference material. The most frequently used are a NIST tin isotope reference solution and the protronic tin metal. So you can imagine that this leads to problems in compare data from different research groups. It's not easy to, or it's not very easy to compare the data without data transformation and recalculation. And also this leads to problems in establishing consistent databases. So that's why we in Mannheim use another isotope value. That's the delta SN value, which is simply the isotopic composition per atomic mass unit instead of using per mil. as a value. And if you have here this, you see this diagram with all the isotope ratios that we have measured, you get you should get this fractionation, this line, this straight line, and delta Sn value is nothing else but the slope of this linear curve, which can be obtained by a regression procedure, for instance. And this value is much more comparable, or the data when you use this value, and the data is much more comparable when you also refer to a common standard, to a common reference material. Of course, different samples have different delta Sn values, and of course. So coming back to a holistic approach, I would like to present to you some practical examples from our project, some case studies. And first of all, I would like to start with this well-known bronze hoard from APA, situated in Romania and dated to the 16th century BC. You see, this hoard contains two swords, 3 axes, and also an arm spiral. So these objects are not directly typologically related. So there are some similarities in the decoration, but basically they are not directly typologically related. And what we did with this fine complex, we simply analyzed or determined the tin and the copper isotope composition and other proxies. And what you can see here in this diagram is we get, and this was very surprising for us, we get this very good correlation in copper and the tin isotope. We also get a correlation in between the tin isotope composition and in this case the nickel concentration, but also the copper isotopes correlate with the trace elemental data, and this is a very good indication in this case that we are here faced with some kind of mixing of the mixing of bronzes in this case, because if you wouldn't have mixed bronzes, we wouldn't get such a correlation in tin and the copper isotopes. So in this case, we can suggest from the isotopic and also from the chemical data that the objects have been produced by mixing and probably by recycling, and more important, that the objects have been produced in the same workshop. And this was very surprising because the objects are not typologically related in any way. So probably we are here faced with the original bronzes, probably. The next hoard that we analyzed, that we investigated, was the famous hoard find from Nebra with the famous sky disk and its associated finds. And in this case, we find a very good correlation between the tin isotope composition and the tin concentration. And what is also clear from this diagram is that the Nebra sky disk, the tin of the Nebra sky disk, is completely different to the objects. So here, different type or different sources of tin have been used for the production of the objects. But this correlation here and also the correlation in this diagram between tin isotopes and the lead isotopes give a very good indication that we are here also faced with the mixing of different sources. In this case, again, mixing of bronzes. A third example is in this case a complex of bronze objects from the late Bronze Age, which have been found on the seabed of the Devon coast of Salcombe and dated to the 12th century BC. And you see here there have been found a lot of swords and pole staves, also weights. And the question was, because the objects have been found scattered on the seabed, the main question was, belong all these objects to the same wrecking event of a ship? or are they completely different? And also, we carried out, in this case, also isotopic and elemental, trace elemental analysis. And what you can see here in this diagram is, again, a correlation in the tin and the copper isotopes. It seems that the bronzes, these are the sorts that we have analyzed, and these are the pore staves that we analyzed, and you see the data in this diagram. And you see, this very good correlation in tin and copper isotopes, and here again, indication of mixing. We also see this in other combinations of parameters. In this case, copper and copper isotope composition and the tin concentration. What we see here is from this diagram, we would expect that the same sources have been used for producing the objects, but here it can clearly be seen that different kind of bronze badges have been used for producing for producing the different objects. And again, indication of mixing and recycling. And most likely the objects were produced in the same workshop. So the objects have been that have been found scattered on the seabed belong in fact together. So in conclusion, stable isotopes, and especially tin, can be used for excluding sources, for excluding tin sources. Copper isotopes give indication of the ore base. I did not directly mention this, but the most important application of stable isotopes in my eyes is it's very useful in the recognition of mixing and recycling processes, especially when you combine different proxies with each other. So from this data, we can establish or reconstruct relationships of artifacts. We can reconstruct metallurgical and trade networks. So I think a high potential of the stable isotopes, or let's say an alternative application of stable isotopes, which is beyond the question of provenance. Anthropogenic fractionation, of course, is unwanted in this case. This is largely true for smelting, casting, and melting, especially for the tin isotopes. But in some cases, anthropogenic fractionation can be helpful in reconstructing, for example, pyrometeorological processes. And we had here a recent study last year in which we tried to figure out if silver isotopes and copper isotopes are helpful in recognition of the ancient gold refining process by cementation with sodium chloride. So it's very difficult to distinguish naturally pure gold or lead, silver pure gold from intentionally purified gold. And we tried to get information about this process by determining the chemical composition of the gold and the stable isotope ratios of silver and copper. And this is the results that we got. You see here, the more silver we remove from the gold that we cemented, the higher, the larger is the fractionation. And when you have a removal of, let's say, 95% or more, you have a very, very large fractionation. This is the same with the copper isotopes. And when you compare this with the natural variation of silver isotopes in gold ore, you see these fractionation or these isotopic values are far beyond natural variation of gold ores, and so it seems possible to recognize the cementation process by analyzing the silver isotope composition and the copper isotope composition. And what we did the next step, we analyzed a couple of objects, of gold objects, and from different time periods. And what you see here in this diagram is that there are a couple of objects, especially gold coins, that are possess isotope silver isotope compositions that lie outside the natural variation, and this is a clear indication for I think this is a clear indication for the use of the cementation process for purifying this this gold, and this is the first time that we have now a tool for recognizing this process. So at last. And the last 2 slides of my presentation. This was the results of the smelting experiments that we carried out with cassiterite. And what you can see here is the isotope composition of the smelted tin. And when we have a look on the slags that we analyzed, where we have heavy isotope enrichment in the slags, and at the same time we got a light isotope enrichment in the evaporated tin fraction. So always when you smelt tin ores, cassiterite, you have a considerable amount of tin evaporated, and this is very light in the isotope composition, and that brought me to the idea: can this isotope fractionation or this light isotope composition be used for the recognition of smelting processes in the environmental record? When we, for example, analyze peat cores of ampromorphic mires. So if we find, if you can be able to find light tin isotope composition in that such peat cores and correlate this with the tin contents of the peat, this can probably be a possibility to reconstruct prehistoric or Bronze Age smelting process in a direct vicinity of this mire. So just an outlook or a perspective for the future. And then with this, I want to thank you for your attention.
Thank you very much, Daniel. Time for 1 or 2 questions?
You showed us that the Nebra sky disk is an outlier for lead and for tin isotopes. Now, at this very moment, the Nebra sky disk is shining in the British Museum as the star, or should I say the moon of the show. Of course, many people wonder if the sky disk is a fake.
Yeah.
What can you just tell us what your present opinion is on this?
So actually, the tin isotopes are different, not the copper not the lead isotope composition. So by means of lead isotopes, they are comparable to the other finds. So they are only the sky disk is only different in the tin isotope composition. But from this result, we cannot exclude or not say if it's authentic or not. So we can only say we have different tin used for the production. So it's not a possibility to authentify the object. But my personal opinion is the object is not a fake. So it's
Anyone else? Anyone? And I will have a go. Tin fractionation, you've mentioned it at the end, after you've excluded a number of sources in. Is it an issue in that exclusion, or is fractionation too limited to be a problem?
It's indeed limited because so we did a lot of experiments, smelting experiments, and we find fractionation on smelting. So, but this is very small, and always more or less in the same range. So when we take the 124 to 120 isotope ratio, it's about 1 point per mil, 0.1 per mil. So that's not that much. And when you always have more or less the same fractionation in the smelting experiment and the smelting operations, you can correct your measured values, and with these corrected values, you can. So I used corrected values for the comparison between the objects and the ores.
Thank you very much, Daniel. Last presentation of the day. Jean Milo on iron isotopes. Thank you.
Okay, sorry. Okay, so for this last presentation, I would like to show you how we can use iron isotope to trace ancient iron, or at least how it can help to determine the provenance of ancient iron objects. So these are part of the results of my PhD. I made between the laboratories JET and TRACE in the University of Toulouse, and directed by Franck Poitrasson, Sandrine Baron, and Marie-Pierre Cousture. So, of course, the appearance of iron in ancient society involved major changes, and the determination of the ancient iron source could help for the restitution of ancient trade networks, and also to better understand the socioeconomic organization of these societies. So to answer this question, we adopted an approach between history, archaeology, and earth science. And we can use different geochemical tools, such as laser system or mass spectrometer with a multi-collector here, in order to analyze the elemental and isotopic composition of ore, slags, and metal samples, so samples collected all along the metallurgical process, in order to find some tracers whose composition will remain unchanged all along this process. So, before the appearance of blast furnace in the Middle Ages, iron was produced in a bloomery furnace. So first ore was extracted, then it was concentrated. It was reduced in a bloomer furnace with charcoal and eventual additives to obtain a slag and an iron bloom, which was then purified by hammering and homogenized by being folding several times, to obtain an iron bar, which was then transformed into different objects. So I will not detail here the corresponding reactions, but the more important here is that the reduction temperature of iron is about 1,300 degrees, which is below the fusion point of iron. So the iron bloom will stay in a pasty state, and some slag inclusion could be trapped into the iron bars and remain into the objects despite the step of purification. And the classical way to trace ancient iron is to analyze the trace element composition within these slag inclusions and to compare this composition with that of slags and ore samples from archaeological sites or ancient mines. So we can determine some pair of elements which will behave similarly during the reduction process, and which will have constant ratio all along the metallurgical process. So in this example here for samarium and neodymium, the samples will plot in distinct lines corresponding to different provenance. So in addition to this trace element analysis, some statistical tools are more and more used to improve the discrimination of on large data set of trace element composition. And here is an example of principal component analysis, which show that for the same sample, it allows for better discrimination of the different sample group. So even it has been already proved very efficient, the problem of analyzing slag inclusion is to find the slag inclusion And so we may have to cut the samples, which could be quite problematic for museum pieces, for example. So in addition, some isotopic tracers have been proposed to trace ancient iron, in particular lead, strontium, and osmium isotopes. So even promising, this approach may have some limitation also, because you can have an heterogeneity within the objects. That's in particular the case for lead. And also you can have a very low concentration. That's the case of osmium, which may involve some complicated analytical techniques. So during my PhD, we proposed the use of iron isotope to try to trace ancient iron. So technically, of course, ores and slag samples were crushed and powdered, whereas the metal samples were collected with a little diamond saw, as you can see here on this entire bar. And so we just need few milligrams to make this kind of analysis. So this is a major advantage of this method. It greatly limits the deterioration of the pieces, the archaeological pieces. So once collected, all these samples are digested into concentrate acid. Then samples are purified, so their iron is purified from the rest of the matrix with a classical chromatography on an anion exchange resin. And then this iron is analyzed using a mass spectrometer with a multi-collection. So we express the iron isotope composition in per mil with a delta index here for 57 iron. It's the ratio between 57 to 54 of the samples compared with that of an international standard. So if this delta is positive, we have a composition enriched in heavy isotopes. If it's negative, the composition is enriched in light isotopes. And because of the natural variability of isotopic variability of iron in ores, and because of the concentration of its composition all along the metallurgical process, that was the first step. Check it during my PhD. We can use iron isotope to discriminate different iron sources. So we applied this approach to the provenance study of Roman bars found in shipwrecks near the French town of Les Saintes-Maries-de-la-Mer. So in this town, more than 20 Roman shipwrecks have been found. They've been dated from the 1st century BC. They contain different types of metal ingots and large quantities of iron bars. And they have been dated of the same period than a Roman iron production in the Montagne Noire, just there. Where you can see here in the site of Les Martis, high concentration of remains of blumerifernates, which attests the importance of this region for iron production in Roman times, and in particular between the 1st BC and the 1st AD. So we test the hypothesis of a provenance from the Montagne Noire for this bar found near Les Saintes-Maries-de-la-Mer. So this bar could have different shapes. Some show some stems, which correspond in fact to different workshops of iron bars production. Their composition vary between steel and soft iron. And previous study tried to test the hypothesis of an origin from the Montagne Noire using trace element analysis and slag inclusions. So here are the results of this study. So we can find different groups. A first group containing the Eros and Lepidus tempered bars, and also an N-stub bar here. They have distinct cesium to rubidium ratio, but similar samarium to erbium ratio, but always included in the variation range of materials from the Montagne Noire here and here in red. So the author conclude to a provenance from the Montagne Noire for these bars. Then we have a second group here with samarium to erbium ratio, which slightly differ from the materials from the Montagne Noire. So here, the provenance from this region cannot be fully validated. And then we have a third group here with very constant trace element ratio for these two covers. and clearly out of the composition range of materials from the Montagne Noire, so the author conclude to another provenance for these bars. So we analyzed the iron-isotope composition of the same bars, and we compare it to materials from the Montagne Noire. So we can find bars from group 1 and 2, sorry. Yeah, so first of all, except for the corroded sample here, and maybe not this one, but all these bars have a very homogeneous iron-isotope composition, as you can see within the dotted lines for each bar. Then we can find the group 1 and 2, which have composition similar to materials from the Montagne Noire, so we can validate a provenance from this region for these bars. And then we have the third group, with each bar having its own iron-isotope composition, some clearly out from the variation range of the Montagne Noire, so we can validate another provenance, but still unknown so far. And here we have two bars with composition similar to that of the Montagne Noire. So here we cannot exclude the major problem for every elemental and isotopic tracer. We can have overlapping composition between distinct sources. And then we also analyze a last bar here, which didn't contain enough slag inclusion to make a trace element analysis. And except for the corroded sample, this bar have composition similar to that of the Montagne Noire. So we suggest a provenance from the Montagne Noire, which is in accordance with the Eros stamp of this bar, like for the green bars here. So now if we compare these two tracing approach, we have group 1 and 2 with distinct cesium to rubidium ratio and similar iron-isotope composition. So here we think this is inherited from the ore source of this bar, which are hydrothermal derived Gaussian from the Montagne Noire. So if we only consider the trace element analysis, we can discriminate different workshops within the same region. And in contrast, the very narrow composition, iron-isotope composition of these bars may allow discrimination at comparison with other regions of iron production, even if, unfortunately, we don't have an extensive database of iron-isotope composition in different regions of iron production. So, in fact, the combination of these two approaches allow discriminating at different scales. And then we have the third group with a very constant trace element ratio, which argue for a single source for these bars, and in contrast, distinct iron-isotope composition. So it could seem in contradiction, but here we propose, in fact, that these bars have a single source of sedimentary iron ores. And it makes sense if we compare the variation range of these bars with that of different types of ores. If you have here, you have the variation range of group 1 and 2 compared with different supergene Gaussian from different places worldwide. And they are of the same order. And in contrast, the variation range of bars from the group 3 is much wider and is of the same order than different types of sedimentary iron ores. So here the hypothesis is that even a single source with a variable iron-isotope composition, so this variability will be reflected in the bars produced with this single source, single sedimentary source. So in this precise case, in fact, the combination of these two tracers provide important information on the nature of the iron ore sources. So it could be very useful to guide archaeological investigation to try to find the source of these bars from group 3. And now, briefly, I would like to show you the comparison of this Roman iron production with the Gallic iron production north to the province, to the Roman province of Narbo Martius. So in fact, we compared the composition of these bars and matters here with that with the composition of Gallic bars found here, which may be related to metallurgical remains in the two sectors of Crespin and Ambialet in the department of the Tarn. And these bars are about the same period than the Roman iron production. So here are the composition of the two Tarn sectors and the materials from the Montagne Noire. And even if there is an important overlapping between these three sectors, the composition of the Gallic bars is very homogeneous and corresponds to the exact mean value of materials from this sector. So at least for this bar, we can suggest a local provenance, maybe from this sector for the Gallic bars. And maybe more interesting here, if we compare the composition of the Gallic bars with that of the Roman bars, a simple t-test shows that they are significantly distinct composition. So in this case, the iron isotopes allow distinguishing two iron production in a very narrow chronological and geographical scales, because in the same time we had in the south, in the Montagne Noire, a Roman iron production which was destined for the iron trade in the Mediterranean Sea, and in the same time we have a Gallic iron production here, which was most likely destined to local diffusion. So to conclude, I don't want to say that iron isotopes are a new magical tracer. I prefer to say it's a new tool in the toolbox for iron tracing. And it presents the great advantage of limiting the damage on archaeological objects, so it can be used to analyze to help determining the provenance of museum objects. Then if we combine trace element and iron isotope analysis, we can make discrimination at different scales. And above all, it provides crucial information on the nature of the corresponding sources. And to finish, something which is really important in my opinion is the archaeological context. Because every provenance study should consist in testing hypotheses based on archaeological and historical indication, because I think it makes no sense to analyze materials or in particular ores from mines which were not actually mined in ancient times. And so taking into account this context may allow greatly limiting the major problem of overlapping composition between the sources. And thank you for your attention.
Questions for Jean? No questions? Yes. Microphone. Yeah. Let's go.
Thank you, Joe. So you said that there are still limitations because of overlapping data in the lead isotopes, you showed it, and also the chemical composition. So in my opinion, it would be beneficial to include also osmium isotopes. So you said it's difficult. There could be challenging to determining the osmium isotope composition of iron, but it's quite easy to do this. So our lab used to use osmium isotopes for metal provenancing, iron provenancing, and it works. So from my opinion, very well. So it could be an additional proxy for discrimination, for better discrimination, even better discrimination.
Yeah, and I agree, because I think the process of isotopic fractionation between iron and osmium are not the same. So maybe I'm not sure, but maybe the composition could reflect, be uncorrelated and reflect different things and bring different informations. But I think for both we have a lack of extensive data on ancient mines. That's the case for iron here, but I think it's also the case for osmium. and we need to create some databases with many composition for many ancient mines. Yeah, that's my opinion.
So the advantage of osmium isotopes is they don't fractionate on the smelting process. So that's a benefit of them. So I'm not sure about iron isotopes. Do they fractionate on smelting?
Not because of the metallurgical processes, just in the ores. In fact, the variability comes from the ores, not
just
from
from the ores, not on the
and that's
processing.
the same for osmium, I think.
They do fractionate on oxidation.
Yeah. You mean if you oxidate the bars, or of course?
Simple rusting.
Oh yeah. But that's the oxidation is the main factor of fractionation in the ores, and of course in the metal. That's why we need the uncorroded metal centers.
It's interesting to see that they fractionate in corrosion, but not in oxidoreduction change in the smelting.
In the smelting, so maybe you can find some differences within bloom, but the fact of hammering and homogenizing the bloom to create a bar, in fact, it homogenizes this composition. And so we check on experiments of ore reduction, and the composition of the slag and the metal was the same than that of the ores.
Other questions? Daniel?
Comment. So, because I remember Patrick, you done this strontium isotope to the iron. So, is that maybe together? Is that what I just my general question? So, why some isotopes is once the developer stop, not just like it's not commonly used. So since like 2007 or so, does that what does that imply? Like for the new technologies, yes.
Why it's not commonly used?
Yes.
I think maybe I'm wrong. But, I think strontium could be impacted by the clay of the furnace. So if the concentration of the strontium concentration is very low in the ore and in the metal, you can have an impact of the materials from the furnace itself. So it could make a confusion. So maybe you can complete my answer.
I promised never to do it again because it was very dirty chemistry and it took a lot of effort to dissolve half artifacts to get the strontium out. And then there is the discussion of possible contamination, etc. But that's the reason why we stopped with it. And iron, of course, to contaminate iron in a pure iron artifact, that would be strong. So it's simpler then. I think it's a more elegant solution.
I wonder if anybody has been using that anyway. Just let me rephrase the question again. I remember a few years ago they tested the use of tungsten isotopes for local provenancing. I wonder if anybody has pushed that. Anyway.
If it works. I don't have the reference, so if you have the reference, it has been published? Or?
Not me.
Didn't you?
It was done by, I think, the custom people. They were leaking the iron.
Okay. Interesting.
Other questions? No? Then I think it is time to move to the final part. Thank you very much, Daniel. Jean, sorry. I was looking at Daniel and then I said Jean. Said Daniel to Jean. No. Anyway, I'm Patrick. Hi. I was asked to summarize a bit, give final remarks on this wonderful, wonderful workshop. And so we received basically 3 questions or 3 purposes at the beginning from the organizers, whom I'd like to thank very much at this point for organizing this. Royal Society of Chemistry, the Society for Antiquaries, Mark Charles and colleagues, thank you very much for bringing us together. And you gave us 3 tasks, basically. The first was, if I remember correctly, to leave our silos and talk to one another, because there is a compartmentalization of bioarchaeology versus the materials people versus the archaeologists and geochemists or chemists. That we certainly did today. There was the state of the art, and then a very specific question on databases. How do we construct them? Are they useful, and how shall we progress? I propose I'll bring up a couple of points from the lectures that we've seen here, and then we have until 5 o'clock to discuss, because there is literally a closing time to this room. So in terms of talking to one another, I think we shouldn't forget in this whole discussion that we are, in fact, or most of us are doing archaeology. We are looking at man in the environment and human behavior. And so what we do can be a scientific exercise in the chemical lab, but it is an old cliche that it should revert back to an archaeological research question, and it is very important here. And to say more, there has been quite an evolution in theoretical frameworks in archaeology, a bit too much perhaps, with object biographies and chaînes opératoires, etc. But our methods that we use and develop are actually offer a unique insight into object biographies. It was mentioned, isotopes have the potential of establishing a relationship between artifacts or within an artifact's production. How is that not object biography or chaîne opératoire study? It is by example such a thing. So perhaps it's a matter of just stressing it to our colleagues archaeologists, but we are in fact doing that. It might be a matter of advertising our own work, but referring back to that archaeology might be useful to get the things done that we want to do. Martin Millet, that it was about people in the environment, the material past, and by example, that is what we do. It's interesting to see that that is what our bioarchaeologists and our material culture people, to call them the inorganic people, do. It was mentioned that we need a holistic approach, or somebody said this is a holistic approach. I believe it's in Isotope. Daniel said that. In fact, it should be the normal approach where we incorporate those. It shouldn't be necessary to say it's a holistic approach. Just define your questions well. And that could offer a help in having disciplines talk to one another. As for state of the art, leaving beside issues of cost, sampling, sample availability, non-invasive analysis, which is a problem and a research field in its own, we've seen a cycle of methods, which I thought was wonderful, where you explore a new method, have optimism, have pessimism, and then instead of discard, which you would do in an object biography, you have realism in applying the method. And we've seen several stages in the systems applied today, and I would call it the method biography, perhaps, instead of the object biography. Carbon and nitrogen in diet reconstruction are established methods. And there you see that because the method is so well understood, the resolution of its application becomes better and better. And it is not simply analyzing bones, you are analyzing single biomolecules in some applications, which again pushes that limit and whether the interpretation can be done or not, and the optimism-pessimism cycle starts again. But when you have this established method, that becomes possible. And for strontium, we've seen that for bioarchaeological applications, strontium carries this geological information. There is still the question of how is it carried from geology to human materials, and then how is that different to plant and animal materials? And that is an important limitation that needs to be stressed. I'll come back to that with the databases. While in the inorganic applications, that geological system is carried on from ore to material unchanged. And so it might be an issue of getting enough material or analyzing it correctly, but the interpretation is much more straightforward. So thank you for that final question on strontium isotopes. That illustrates it well. For lead, it seems to be the inverse, that geological information in pre-industrial society, when we do not take into account pollution, which was shown that from the modern era, from the Roman era, needs to be taken into account, in human applications and animal applications, that seem to be a straightforward one-to-one relationship. While for our In organic people, this is slightly more complex, the interpretation of lead isotopes, and an ongoing debate where an interesting parallel to genetics could be drawn of all people hating each other. That has, fortunately, been solved somewhat. No longer we have the 80s fistfights in conferences, but you should be careful. It was interesting to see that some of our systems applied, like oxygen, like copper, silver, iron perhaps, have a lower precision of assignment. They might work well, but they are more limited in their capability of interpreting, whether it is climatic information or geological information that is conveyed. It puts a certain limitation to what you can do with the method. And perhaps that optimism, when we know the system well, should not be converted to pessimism, but to realism immediately, certainly in use of those systems, say from a database to an artifact by someone who doesn't know the technique very well. And then we have, there was mention of tungsten. There's many other systems that are being explored, a one-off versus a couple of applications. We've spoken about tin, where there is geological information, where there is possibly an issue of fractionation, but there's simply so much overlap that its application is perhaps limited. Though I would say that tin goes back to what we really need to do with these isotopic systems. And at the start, that became very clear. This is exclusive only. Only with certainty can we exclude a source. And that went, as the talks went along, went to more and more optimism of it's this one. But that all depended on, and certainly when we excellently shown with the iron isotopes, when you have the archaeological information and you know, look, it's this area, we have a number of ores that are possible, it's this archaeological, chronological, geographical frame, yes, then it becomes possible. Again, talking to our colleagues there and incorporating that archaeological context, apart from the geological background, which has been stressed each and every time we need to understand the geology, we need to understand that archaeological context, certainly. And it becomes very important when we want to carry that information to databases that are easy to use and hence easy to spit out numbers for interpretation, that interpretation is correct and according to what you can do with the system. And so that is different for carbon, nitrogen, which would be a standard application. Strontium, lead, perhaps, depending on the material you're looking at, could be standard. For copper, silver, iron, oxygen, there are limitations, and they are perhaps easier to understand in the sense of, yes, we can discriminate certain factors within the area. For other systems, such as tin, antimony, which I'm doing myself, where you are wondering whether what you're seeing actually, are you looking at fractionation technology? Are you looking at provenance? How is that interpretation even possible? Perhaps it is too early for such databases because comparability, applicability, modeling of fractionation, simply knowing what you're doing is not established enough. And there, the call would be, there's simply not enough labs doing those systems. And it is perhaps an issue of funding bodies. If you develop a new system, you have a publication because you are the first to apply antimony, boron, I don't know which system, tungsten, to a material. And that will give you a publication. And then that sort of precludes all your colleagues from doing it again because you're simply checking somebody else's work. But certainly with systems that fractionate, that we don't know what the overlap is, what technology, what provenance information is in there, that check is absolutely necessary. Even as we are in the Royal Society of Chemistry, thermodynamic modeling of fractionation might be useful in some of these systems to know what is theoretically possible, what can happen in such a system, like smelting, like changing of signatures in certain reactions, in certain processes. With which I come to my final third question, the databases. Databases require maintenance. Databases require not only technical maintenance, but they require academic maintenance. In in expressing what you can do with the database. We've seen that in interpreting these isotopic systems, probabilistic approaches were often more useful than, and more realistic, I'd say, than other approaches, and often they are mathematically more correct. There is the whole debate on lead isotopes, whether you use biplots, kernel densities, or model ages to interpret lead isotopes in looking at inorganic materials, in particular metallurgy. Model ages gives you geological information which is extremely useful. I've heard the mention of it using as checking whether your data are actually any good, whether they are consistent with a certain ore origin. If to answer archaeological questions, I think they haven't proven their worth yet in giving extra information versus biplots. Kernel density is the same. They are mathematically more correct, theoretically, but in application, perhaps they give us simply the same information as biplots. And so perhaps it might be for that database academic maintenance interesting to explore those avenues. And we've seen the absolute exemplary initiative of Global ID, or Global ID, I don't know how to pronounce it, Global ID, okay. And we've seen other databases being established with isoscapes that provide that opportunity to check that, to look into those roles. Projects are finite, though, and how to keep such database and such discussion around the database active is a challenge. Perhaps there is a role for museums or learned societies such as these to maintain that role. They are often institutions that have been there for decades, centuries, and that have a much more stable approach to these research questions and possibilities to approach these research questions if they find them relevant, than a ERC-funded project, which we've seen a couple of times today, or than a university project, which is limited in time and resources. And so I find myself sometimes in the discussion what the relevance of museums is. Not so much in society, but what scientists in museums do, apart from dusting off the objects. And perhaps this is something that could help some of these institutions in, look, we are not only the guardians of objects, but also the guardians of data around these objects. It is an interesting discussion to be had what the role of, for instance, museums or societies could be. Apart from what GlobalID has presented, which is absolutely exemplary, which data are crucial? Quality of the database, standardization of the data, visualization, and then coming to interpretation, statistics, processing, which is most valuable, is a discussion to be had. And also, I love the line, what is proper reporting? How do you report something? What do you need to be able to interpret? Citing the limiting factors, bringing together partial data, and interpreting these in a way that makes absolute sense. To come to archaeological models instead of simply sheets of data, which are no use in the communications between our disciplines. Quickly checking my notes. Interesting as well. Modern versus archaeological interpretation is very different. Certainly we've seen this in the bio approaches. If we interpret some modern material, it often gives us a very different look at our databases or our interpretation than the ancient one. I think that is a very important message that should not be discarded. We're looking at more and more forensic application, modern day application, industrial applications even of these. If we start from the wrong foot and interpret the wrong thing, that might not be beneficial for our field. And then bigger is not necessarily better, was an important message as well. Localized studies that are well-defined are more effective, have more impact. If you know from the onset what you are doing, that might improve your final results. And as a final remark, it might be an interesting thing to explore as well, how all these collection of data, bringing together of data, might be combined in a system that not only has one isotopic system and reference data for it, but possibly several isotopic systems, and interpreting them to organic versus inorganic data. That interpretation is very, very different. And by clicking a couple of boxes, you might get lists and lists and lists of data, but you might not necessarily be comparing, be it in a big sweep or in a localized study, the right thing to the right thing. And that is something, the right artifact type to the right reference data. And that is something that cannot easily be resolved in a project where a database is, as it should be, fair, but is also easily accessible. And so perhaps the role there lies with reviewers of publications, but that is a whole different discussion. I think we have at least 15 minutes left for you to criticize me on my summary and to give different suggestions. Please, also online. Who wants to go? I think we have, oh, you're second now.
I've been really struck by how relevant this is to what is happening now in the world. Because you spoke today about authenticity, privacy issues, also provenance, ownership, responsibility, colonization, and custodianship. But really, from going back thousands of years, the war, military, and migrations, this is what we are seeing now, and how it's impacted on the food supply, the diet, cultural development, pollution, in fact. But I think I'll just finish by saying that this meeting now will be remarked on for its collaboration after a very difficult period of time of pandemic as well.
Oh, yes.
Which we haven't spoken about, but perhaps in the future. Thank you.
Thank you very much. There are no alternate facts. There are no alternate data. There are only alternate interpretations.
Can I take you up on your point about museums?
Yes.
The Ashmolean Museum in Oxford was very good at putting together and maintaining databases until there was a change in management at the top and a change in fashion. And suddenly, without any real warning, they ceased to maintain these databases, which had been the result of good research. And I think museum curators at the academic research level are very vulnerable to fashion and money and the getting people over the threshold. So I think we need to be wary about relying on museums in this respect.
Thank you very much for that warning. The Ashmolean, of course, is a research museum in the best sense. Yes. Well, you say was, yes. I shouldn't comment. But it is, of course, true for universities as well, where that can happen. I think if it is a core business, it might be better protected and seen as such in a mission statement. But then we might be looking at more academic societies as well, who are perhaps more stable than museums. It is an inherent danger to all research, I'm afraid.
It goes higher than that, though. You look at something in Norway at the moment with this amazing sort of thing. Thanks, Patrick. It goes even higher up to governments, like what might be happening in Norway at the moment over the Viking Ship Museum, which is under threat because of the whims of one particular minister. Norway's national treasure is almost it's unbelievable, really. What is happening there, which is very worrying. So it's not just at the museum level or university level. I mean, I've got the microphone as far as databases are concerned and curatorship and whatever. One of the reasons why holding this meeting here, the Royal Society of Chemistry, and I'm going to watch what I say here very carefully, but is to perhaps persuade the powers that may be here at the RSC. They could have some sort of role in this, and we've had one or two discussions already without wanting to tread on the toes of other databases and things which are going, but maybe there's a responsible role that we can play to avoid particularly brought out the frustrations and things that's going on. But yeah, I think all of us here are aware of the problem. Now, something might be done. Yeah.
Thank you. Also, multiple custodians, of course, might be the answer to, if there is not one copy in one place, it might be more easy to...
Exactly, when one's under threat, it doesn't matter because there's a cartel.
Yes,
which
I don't know how that technically is possible, but it would be an intellectual...
You said this couldn't happen in the 1980s when everyone was tearing each other to bits, and it's not just this field. In my own home field of hydrodynamics, this was going on in the 1980s, and now things seem to have calmed down, although not in genetics by the comments of Mark.
There's more money in genetics, that might have something to do with it.
But I think that will also blow over in time too, where there's a mood now, people working together. Maybe this is a feature of post-COVID. I don't know.
Thank you. Right. I'll pass the microphone. Gets me my fitness done.
Thank you very much. So I first wanted to say how enjoyable today's been and how interesting, but also that I'm really struck by how little we've talked about migrations, which I see as a good thing as an archaeologist, because certainly when these techniques were sort of initially developed, that really was the core of the questions, and it's clear that they are much, much more interesting than that. And that we're starting to get much more circumspect about how you can interpret them, which is a really good thing. And I can't remember which talk it was, but I think it was the DNA one that talked about these frameworks as political. And that is so important to bear in mind. I think I've lost count of the number of papers, quite often DNA, but sometimes isotopic, where the fact of movement apparently being demonstrated is presented as the answer to all cultural change. And that's just so inadequate in terms of a theoretical position. So it's really just a plea for people to keep talking to archaeological colleagues, synthetic colleagues, about those much, much broader political and historical frameworks, because they really do matter in terms of interpreting this material.
Thank you. Migration, of course, fits well into a modern political debate which is not without bias. So
no, particularly when you're talking about the origins of the English, which is what I work on.
I couldn't possibly comment. I think we have, yes.
Well, this might be a quick one. Maybe have to shout because we want to let the AV man go.
Okay, sure.
You can keep talking, but without the microphone.
Since you talked about the issue of standardization, in Germany we have now a pretty big project starting, hopefully, or being financed, the NFDI or NFDI for objects, which is one of many. There's NFDI for medicine, NFDI for humanities, and whatever, which all tries, since Germany has the problem that culture is not federal but state-based, that all the different, and I mean, in some ways you have that issue in Great Britain as well, that all states are doing their own thing. The heritage offices, the universities, and there's this initiative, and I honestly don't know where this is going to go because there's so many people involved, to get standards and databases in somehow on one level. And hopefully, or maybe if something comes out of this, this could be an example for other countries as well, to pick up on that in that regard. And there will be certainly something in that regard also on isotopes. I mean, pretty much everybody here coming from Germany is somehow involved with this initiative as well. Just to see, I hope there's something coming out of this. With these huge projects, you never know.
Thank you very much for that comment. Yeah.
10 seconds. We are allowed to continue talking, but Brian, who's been looking after our audiovisuals, has got to go now. So I think we should just thank him because you managed to get the Zoom people able to hear us. They've all been, we've said goodbye to them. We can stay here and talk, but we'll no longer be being broadcast.
Thank you, Brian.
Thank you, Brian.